Java remote method invocation architecture. Here you can see the architectural diagram of Java remote method invocation. In computing the Java remote method invocation, Java RMI is a Java API that performs remote method invocation, the object-oriented equivalent of remote procedure calls, RPC. With support for direct transfer of serialized Java classes, and distributed garbage collection. Here you can see a system architecture. The system consists of three basic layers: the stub, skeleton, remote reference layer, and transport. The specific interface and protocols define the boundary at each layer. Thus, each layer is independent of the next, can be replaced by an alternative implementation without affecting the other layers in the system. For example, current transport implementation is TCP based using the Java socket, but transport based on UDP could be used interchangeably. To accomplish transparent transmission of object from one address space to another, technique of pickling designed specifically for Java is used. Another technique that we call dynamic stub loading is used to support client-side stub, which implement the same set of remote interfaces as a remote object itself. Since a stub of exact type is available to the client of a remote object, the client can use objects built in operators for casting and type checking remote interfaces. Architectural overview. The three layers of RMI system consist of following: stub skeletons, client-side stub proxies, and server-side skeleton dispatchers. Remote reference layer, invocation behavior and reference semantics, unicast, multicast. Transport, connection setup and management, and remote object tracking. The application layer sits on top of the RMI system here. This figure is an illustration of layers of RMI system. A remote method invocation from a client to a remote server objects travels down through the layers of the RMI system to the client side transport, then up through the server side transport to the server. The rest of this discussion here summarizes the functionality at each layer in the system. A client invoking a method on a remote server object actually makes a use of a stub or proxy for the remote object as a conduit to the remote object. A client held references to a remote object is a reference to a local stub. Thus, stub is an implementation of the remote interfaces of the remote object and forwards invocation request to the server object via remote reference layer. The remote reference layer is responsible for carrying out semantics of the layer of the type of invocation. For example, this layer is responsible for handling unicast or multicast invocation to the server. Each remote object implementation chooses its own invocation semantics, whether communication to the server is unicast or the server is part of a multi-class group to accomplish server replication. Also handled by the remote reference layer are the reference semantics for the server. For example, the remote reference reference layers handles live and or persist references to remote object. Persistent object references are required in order to activate objects to support long-running servers. Transport is responsible for connection setup with remote locations and connection management, and also keeping track of and dispatching to remote objects the targets of remote calls residing in the transport's local address space. In order to dispatch to a remote object, the server's transport forwards the remote call up to the remote reference layer specific to the server. The remote reference layer handles any server-side behavior that needs to be done before handling of the request to the server-side skeleton. The skeleton for the remote object makes up the call to the remote object implementation which carried out actual method call. Return value of the call is sent back through the skeleton remote reference layer, then and transport on the server side, then up through the transport remote reference layer and stub on the client side. Stub skeleton layer. The stub skeleton layer is the interface between the application layer and the rest of the RMI system. This layer does not deal with specifies of any transport, but transmits data to the remote reference layer via abstraction of Marshall streams. Marshall streams employ a mechanism called pickling, which enables Java objects to be transmitted between address spaces. Objects transmitted using the pickling system are passed a copy to the remote address space. Stubs for remote object is the client-side proxy for remote object. Such a stub implements all interfaces that are supported by the remote object implementation. Client-side stub is responsible for initiating a call to the remote object by calling remote reference layer, marshalling argument to a Marshall stream obtained from the remote reference layer, informing remote reference layer that the call should be invoked, unmarshalling the return value from the Marshall stream, informing remote reference layer that the call is complete. The skeleton for the remote object is a server-side entity that contains the method which dispatches call to the actual remote object implementation. The skeleton is responsible for marshalling, unmarshalling argument from the Marshall streams, making the up call to a actual remote object implementation. The skeleton here, marshalling the return value of the call onto the Marshall stream. Remote reference layer. The remote reference layer deals with the lower level transport interface. This layer is also responsible for carrying out a specific invocation protocol which is independent of the client side stubs and server skeletons. Each remote object implementation chooses its own invocation protocol that operates on its behalf. Such an invocation protocol is fixed for the life of the object. Various invocation protocols can be carried out at this layer. For example, unicast invocation, multicast invocation, support for specific replication strategy, support for persistent reference to a remote object, enabling activation of the remote object, reconnection strategies if the remote object becomes inaccessible. These invocation protocols are not mutually exclusive but may be combined. For example, a remote object may require both persistent reference semantics and replication. Both of these protocols could be carried out in the remote reference layer. Invocation protocol is divided into two cooperating components, the client side and the server side components. The client side components contains information specific to the remote server or servers if invocation is to a multicast group, and communications via the transport to the server side component. During each method invocation, the client and server side components are given a chance to intervene in order to accomplish the specific invocation and reference semantics. For example, if a remote object is part of a multiclass group, the client side component can forward the invocation to a multiclass group rather than a single remote object. A corresponding manner, the server-side component is given a chance to intervene before delivering a remote method invocation to the skeleton. This component, for example, could handle ensuring atomic multicast delivery by communicating with other replicas in the multicast group. The remote reference layer transmits data to the transport layer via abstraction of a stream-oriented connection. The transport layer take care of the implementation deals with the implementation details of the connections. Although connections present a stream-based interface, a connectionless transport may actually be implemented beneath the abstraction. Transport. In general, the transport of the RMI system is responsible for setting up connections to remote address space, managing connections, monitoring connection liveness, listening for incoming calls, maintaining a table of remote objects that reside in the local address space, setting up a connection for an incoming call, locating the dispatcher for targeting for the target of the remote call, and passing the connection to this dispatcher. The connection representation of the remote object reference consists of an endpoint and an object identifier. We call this representation live reference. Thus, given a live reference for the remote object, the transport can use the endpoint to set up communication channel to the address space in which the remote object resides. On the server side, the transport uses the object identifier to look up target of the remote call. The transport of the RMI system consists of 4 basic abstractions based somewhat on the transport of modular 3 network object system. Endpoint. An endpoint denotes an address space. In the implementation, endpoint can be mapped to its transport. This is given in endpoint. A specific transport instance can be obtained. To transport, the transport abstraction manages channels. Each channel is a virtual connection between 2 address spaces. Within a transport, only one channel exists per pair of address spaces, the local address space and the remote address space. Given an endpoint to a remote address space, a transport setups a channel to that address space. The transport abstraction is also responsible for accepting calls on incoming connections to an address space and setting up a connection object for call and dispatching to higher layers in the system. 3. Channel. Abstractly, a channel is the conduct between 2 address spaces. As such, it's responsible for managing connections between local address space and the remote address space for which it is a channel. For a connection is the abstraction for transferring data, performing input or output. Transport layer define what the concrete representation of an endpoint is, so multiple transport implementations may exist. The design and implementation is also allow multiple transports per address space, so both TCP and UDP can be supported in the same address space. Thus a client and server transports can negotiate to find a common transport between them. Here you can see client program interacts with stubs and skeleton. Here server program interacts with stubs and skeletons layer. Here the client program interacts with the stubs and skeleton layer, and server program also interacts with its stubs and skeleton layer. Stubs and skeleton layer interacts with remote reference layer. Remote reference layer interacts with transport layer. Here the RMI system consists of stubs and skeletons layer, remote reference layer, and transport layer. Here you can see Java RMI architecture in a different view. In a distributed system, applications run in all different machines in a network. These applications need to communicate with each other and each other to send commands and exchange computation results from time to time. A socket is the basic communication mechanism that is supported by almost every programming language and operating system. Sockets are highly flexible, but they are at a level that is too low for developers, because new protocols need to be designed for specific purposes, and they need to encode and decode messages, for example. Java platform provides developers with Java RMI, which utilizes features such as dynamic class loading and reflection of Java, and uses a stub object to manage the method invocations. Developers simply create a stub that is used to make method invocations, which takes care of marshalling and invocation and sending it to the remote RMI server. From developer's viewpoint, this is just like calling a remote object. Architecture of RMI is shown here. All RMI servers register with the registry server of their hosting remote object. RMI clients first look up stubs of a remote object on the registry server, which they subsequently use to call their corresponding remote objects. Stub is very important in Java RMI. It acts as a remote object to the client application by implementing the same interface as the remote object. The client application invokes methods on a stub, and the stub will carry out the methods call on the remote object. It marshals the parameters to the remote JVM, wait for the results, and unmarshals the return value and returns the result to the application. In this work, this application, so here you can see stub and transport are inside client. Here stub and transports are inside client. Clients interacts with its registry. Transport interacts with server here. Here transports interact with server via RMI. Here client interacts with registry and retrieve stubs. Here you can see an RMI distributed application that uses RMI registry to obtain a reference to a remote object. In an overview of RMI applications here. RMI applications often comprise two separate programs, a server and a client. Typical server programs create some remote objects, makes references to this object accessible, and wait for clients to invoke methods on these objects. A typical client program obtain a remote reference to one or more remote objects on a server and then invokes method on them. RMI provides mechanism by which the server and client communicate and pass information back and forth. Such application is sometimes referred to as distributed object application. Distributed object applications need to do following: locate remote object. Applications can use various mechanisms to obtain references to remote objects. For example, an application can register its remote objects with a simple naming facility, the RMI registry. Alternatively, an application can pass and return remote object references as part of other remote invocations. Next point is communicate with remote objects. Details of the communication between remote objects are handled by RMI. To the programmer, remote communication looks similar to regular Java method invocations. Next point, load class definition for objects that are passed around. Because RMI enables object to be passed back and forth, it provides mechanism for loading an object class definitions as well as transmitting an object data. This illustration depicts an RMI distributed application that uses RMI registry to obtain a reference to a remote object. The server calls the registry to associate or bind a name with the remote object. Clients look up the remote object by its name in the server's registry and then invokes a method on it. This illustration also shows that an RMI system uses an existing web server to load class definitions from the server to client and from client to server, from client to server, from object when needed. Here you can see RMI client is connected to RMI registry via RMI, and RMI client is connected to RMI server via RMI, and RMI client is connected to web server via URL protocol, and RMI server is connected to web server via RMI URL protocol here, and RMI server is connected to RMI registry via RMI, and RMI registry is connected to web server via URL protocol here. Here you can see RMI architecture stack and participating classes or interfaces in RMI client server programs. As RMI is an action of invoking method of a remote object from another address space JVM or machine. Its characteristics differ from local method invocation. We analyze the characteristics which differ in local method and remote method invocations, and how RMI implementation RMI implements these characteristics. The RMI architects try to make the use of distributed Java objects the architecture is built using 3 layers. Stub and skeleton layer, which lies just beneath the view of programmer. In this layer, RMI uses proxy design pattern, remote reference layer, which connects clients to remote service object, running on server machine. Transport layer, which provides basic connectivity between JVMs. The comparison of you can compare RMI layers with the comparison of RMI layers with OSI layers shown in this figure. We have also identified the participating Java classes at each layer of Sun RMI implementation. Each layer of RMI implements its own interface. These layers are independent of each other, so can be replaced by other implementation without affecting other layers. The basic components in any RMI applications are interface, RMI server program, RMI server program, the basic components in any RMI applications are interface, RMI service program, RMI client program, stub, skeleton, and RMI registry. Before a client can use a remote service object, the remote object must be instantiated on the server and exported to RMI registry. The RMI server program will bind the remote service with RMI registry. The interface and remote service, the RMI architecture separates out the definition of behavior and implementation of that behavior. The code that defines the behavior and the code that implements the behavior are separate and run on separate JVMs. The definition of behavior is given by the interface, and implementation of behavior by Java class. In Java, it is responsible to have 2 implementation classes of the same behavior interface. RMI supports two classes that implement the same interface. First class is the real implementation of the behavior, which runs on the server machine, called the remote service object. The second class acts as a proxy for the remote service and runs on the client machine. Stub skeleton layer. RMI uses proxy design pattern at this layer. Using proxy design pattern, object in this in one context is represented by another proxy in a separate context. A stub is a client-side proxy for remote service object. Server-side proxy is known as skeleton. The stub understands how to communicate with the skeleton across the link. Stub intercepts each method call by client to remote service. The stub provides functionalities of one, carrying out conversation with skeleton, 2, marshalling of argument, 3, marshalling out result, for providing result to the client program. The skeleton understands how to communicate with stub. Skeleton is responsible for carrying out conversation with stub, reading and unmarshalling parameters for the method call, delegating the call to the remote service implementation, accepting and marshalling the return value of call, sending the result back to the stub. Remote reference layer. Remote reference layer handles semantics of invocation. JDK 1.1 implementation of RMI provides only unicast, point-to-point and connection between client and remote service. In JDK 2, this layer is enhanced to support the activation of dormant remote objects. When a method call is made by a proxy client, the RMI determines if the proxy service object is dominant. If the dormant RMI will instantiate the object and restores its state from disk file. Other types of communication semantics are possible. For example, using multicast semantics, a single proxy could invoke multiple remote services in replicated objects. Transport layer. Transport layer provides basic connectivity between JVMs using stream-based TCP network connections. RMI uses Java Remote Method Protocol, JRMP, RMI specification 1999, via protocol on top of TCP/IP. JRMP is a proprietary protocol. The first version of JRMP, which was released in JDK 1.1, requires the use of skeleton classes on server side, whereas the second version released with JDK 2 has been optimized for performance and it does not require skeleton classes. This layer is responsible for setting up connection to remote address space, to managing and monitoring the connection aliveness, 3, listening for incoming call, for multiplexing multiple virtual connections with single TCP connection. Direction of internal working of RMI. Possible enhancements and implementing authentication is in standard RMI, Java RMI. Here you can see RMI client and RMI server here. Here you can see client program and server program. Here RMI client stub, here server skeleton. Client stub, remote object and remote stub are in client stub. Here client stub, remote object, and remote stub in server skeleton. Here you can see below that client stub interacts with the remote reference layer, and server skeleton interacts with remote reference layer. Remote ref, unicast ref, unicast server ref, and live ref are in remote reference layer. Remote reference layer interacts with transport layer, endpoint channel, endpoint channel, TCP endpoint, TCP channel, TCP connection, and TCP transport are inside transport layer. Here the you can see OSI layers, client program and server program are in application layer. Client stub and server skeleton are in presentation. Remote reference layer and is in session, and transport layer is in transport. Here transport layer of client, RMI client, interacts with transport layer of RMI server. Here you can see RMI communication process. Dissection of internal working of RMI, possible enhancements, and implementing authentication in standard Java RMI. One here, first of all, RMI registry should be started on the server machine. RMI registry is also a remote service object. All remote objects exported themselves to an arbitrary point. RMI registry export itself to a default port 1099 to establish bootstrapping. 2. The server program has to create an instance of the remote service object. 3. Remote object should be exported at runtime. For this, the remote object makes a call to RMI runtime to export itself. In this process, the proxy for the remote object is created on the server machine. The remote object makes a remote call to RMI registry to register its proxy. At this point, the RMI registry will have the proxy of the remote object. 4. Client connects to RMI registry. 5. After this, client look up for the service by passing the public name of the remote object as a parameter. The RMI registry return the appropriate proxy stub object to the client. At this point, the client has the stub for remote object. The stub object contains the information about hostname, and port number to which the remote object listens. The remote object can now accept connection from the client. 6. Client calls remote method on the stub object. 7. Client side stub will delegate this call to skeleton of the remote object. 8. The dispatch method of skeleton is called. It uses an appropriate method call on remote object. 9. The method execution of remote object finishes, and the result is returned via skeleton to stub client program. If method throws an exception, then it should be marshaled instead of resulting the same path. This process is explained in this figure. The remote object class has to either extend the unicast remote object class or call static method export object of unicast remote object of RMI linking and remote object initialization. The latest RMI specification, RMI specification 1999, include creation of stub from remote interface. In traditional RMI communication, the client needs stub class file for its working. We discuss here two scenarios of providing stub class file to traditional RMI client. Scenario 1, download stub locally using class path. If the class definition for stub instance can be found locally in class path of the client, the stub will be loaded locally. Scenario 2, download stub dynamically by setting code-based property on the remote object. Code-base in place, which defines the location for downloading classes into virtual machine. The class path can be considered as local code base. If the class definition for stub is not found in the class path of the client will attempt to retrieve the class from the remote object's code base. The client uses URL annotated using a stub instance to download the stub class from its location, registry or web server. Here you can see RMI client, you can see the registry machine. Registry machine interacts with client machine. Here is client and stub inside client machine. Client machine here connected to a server machine. Server, skeleton and remote object are inside server machine, and server machine is connected to registry machine here. Step 1 here, start RMI registry in registry machine. Step 2, create here the start RMI registry in registry machine. Step 1. Here server is connected to remote object via create remote object in step 2. Step 3, server machine is connected to registry machine via server registers remote object. Step 4, client machine is connected to registry machine via connect. And step 5a, client machine is connected to registry machine via lookup for stub. And step 5b, registry machine is connected to client machine via return stub object. Step 6, client is connected to stub via remote calls remote. Step 7, stub is connected to skeleton via delegate call. Step 8 here, skeleton is connected to remote object via method call. Here you can see here sequence diagram showing steps of creating a live ref object. And we are considering dissection of RMI working. Here we discuss about involved objects. In RMI, transfer of data between two address spaces is represented by the concept of connection. Connections between local address space and remote address space is managed by channel. Management of channel is done by transport. An address of space JVM is represented by concept of an endpoint. An endpoint can be mapped to its transport. A remote reference is a pointer to proxy object stub in a local heap. That stub contains information that allows it to connect to a remote object which contains the implementation of the method. Remote object reference includes two concepts: an endpoint. First is an endpoint, and two, the object identifier. This representation of remote object reference is called live reference. When a live reference is given for a remote object, a transport can use the endpoint to establish a connection to address space. In which the remote object resides. The transport on server side uses object identifier to look up the target of the remote call. Object of unicast server ref class is the representation of proxy of remote object on the server space. As shown in this figure, JDK2 implementation includes endpoint, channel, and connection as interfaces at transport layer. And TCP endpoint, TCP channel, and TCP connection as implementation class of these interfaces. The remote ref is an interface at remote reference layer, and unicast ref and unicast server ref are implementation classes of this interface. Object of unicast server ref class is the representation of proxy of remote object on the server address space. This figure explains the steps of creating a live ref object for remote object. Here you can see a RobJ my object, unicast remote object, and use a unicast server ref. Here LR live ref and old object ID, and here TCP endpoint and AP TCP endpoint. Here the RobJ of my object is connected to unicast remote object via super method, and this has a it calls this port integer with the constructor and to itself, and then it's unicast remote object is connected to itself via export object remote and port int returns remote here. Unicast remote object is connected to unicast server ref here via unicast server ref port int, and unicast server ref is connected to the USR of unicast server ref is connected to LR of live ref via live ref port int here method, and say LR of live ref has a object ID method here. Sorry, LR of live ref is connected to old object ID via object ID method here, and then live ref is connected to itself via this old object ID port int here method. And LR live of live ref is connected to TCP endpoint via get local endpoint port int and returns endpoint here, and get local endpoint port int null RMI client factory null remote socket server factory, and returns TCP endpoint here. And here TCP endpoint is connected to here, TCP endpoint here this is connected to TCP endpoint via string port int here, and CFS RMI client socket factory here TCP endpoint host string and port int CSF remote client socket factory, SSF RMI server socket factory, and here SP TCP endpoint, and here you can see it's connected back to TCP endpoint. Here TCP endpoint is connected to LR live ref via return EP, and this is connected to this old object EP endpoint true boolean, and is connected to here, then the connected back to live ref. Now we are considering a dissection of exporting the object. Here you can see sequence diagram showing steps of exporting remote object. The process of exporting object can be divided into two basic steps: creation of live ref for the remote object, to exporting remote object. To provide automatic exporting of remote object, the unicast remote object class is used as the base class for remote object. Once the object of live ref is created for remote object, it is passed to the constructor of unicast ref class, and after object of unicast server ref get created, after that the object of unicast server ref is get created. This figure explains the steps of exporting remote object. TCP transport create the server socket listening mode for TCP endpoint class and inner class accept loop. TCP transport is an active class that wait for new client connection request. When a new connection request arrive, TCP transport create a new instance of uh, connection handler class. By passing the socket, which returns as a result of accept of server socket and string representation of inet address. Socket.get inet address. It receives the connection calls and delegates the calls to Unicast's server ref. Then it calls the skeleton to dispatch the invocation. The skeleton returns the result using the instance of stream remote call class. Created during the remote method invocation. The naming.rebind method, which is called in the server program, takes an argument type of reference of remote object. The naming class construct an object of stub and bind it to RMI registry objects. Following steps explain the process of exporting an object. One naming class uses getClass method to get the name of the class for the remote object. Two, it appends underscore stub to the name of the class to get stub name. 3, it loads the stub class from JVM. 4, it gets an object of remote ref. Method, object of a remote ref from the reference from the remote object by calling getRef method, which passed as an argument to naming.rebind method. The remote ref object represent the mid handle for the remote object. This the reference to the remote object encapsulate all details about remote service object, service server, such as services hostname, listening port, and so on. 5, it uses the object of remote ref created in step 4 to construct stub of remote object. Each stub contains an instance of class implementing remote ref interface. 6, it passes the stub object created in step 5 and public name of remote service object of RMI registry for binding. RMI registry gets the public name and stub object in a table structure. Now we are considering dissection of invoking remote method. For Java RMI client to for a Java RMI client to connect to a remote Java RMI service, the client must first hold a reference to a remote service object. The naming.lookup method is the most common mechanism by which the client initially obtain references to the remote services. Naming.lookup returns the reference to the remote object. This reference is of type remote ref interface. On the client side, Unicast ref class is an implementation of remote ref, whereas on the server side it's the Unicast server ref. Every remote reference contains a server hostname and a port number that allows client to locate the virtual machine VM that is serving a particular remote object. Following steps explain the process of invoking a remote method. Once we have reference to an object of Unicast ref, internally its get channel method will be called, which returns the object of TCP channel class. Dissection of internal working of RMI, possible enhancement of authentication in standard Java RMI. 2, then new connection method of TCP channel class. will be called, inside which the array list of existing trees existing free TCP connection will be checked. If it finds the free TCP connection, it will remove that connection from array list and return it. 3. If it does not get the free connection, then create connection method of TCP channel class will be called, which create a new TCP connection and socket instances. When there is no connection available, then it will write the transport header information to output stream of TCP connection. 4. Object of stream remote call class will be created, which writes remote call header and object ID in the remote object. 5. All method arguments are marshaled according to their type, then return to the output stream of TCP connection. The execute call method of the stream remote call object will be called, which will wait for getting magic number of successful execution of remote method. RMI specification defines both single op and stream protocol for RMI calls. The single op allows the single RMI call to made on a socket, which is then closed. The stream allows the multiple RMI calls. Sans RMI implementation uses stream protocol, which allows the client-side stub object to make multiple RMI calls by opening a single socket. Multiple stub within the same JVM or different JVM on the same host will each have their own socket to server. If client has multiple stub pointing to same server object, same server object, the client will have multiple sockets open to that server. Here you can see ROPJ my object, unicast remote object, USR unicast server ref, unicast ref, LR live ref, util proxy, ROIH LH ROIH remote object invocation handler, EP TCP endpoint. Here you can see a USR unicast server ref is connected to unicast ref via super LR live ref, and unicast ref is connected to USR unicast server ref. And here unicast remote object is connected to server is connected is port object rob j remote USR unicast server ref and return remote. Here unicast remote object is connected to USR unicast server ref, export via export object remote null object false boolean returns remote. And here USR unicast server ref is connected to robj my object via get class method returns class. Here robj my object is connected to connected to USR unicast server ref via return C. Here USR unicast server ref is connected to util via create proxy C class ref remote ref host. Stub is boolean returns remote. Here util is connected to ROIH remote object remote obj invocation handler via remote object invocation, obj invocation handler, ref, remote ref. And here util is connected to proxy via new proxy instance, C class loaders, AC class, ROIH remote obj invocation handler remote, and proxy is connected to util via return remote 1, and util is connected to unicast server ref via return remote 1. Here USR unicast server ref is connected to T target via target remote this unicast server ref remote remote object obj id object obj id true flag. Here and then USR unicast server ref is connected to LR live ref via export object T target void, and LR live ref is connected to EP TCP endpoint via export object one target void, and here create server socket listening mode using TCP transport, TCP endpoint, and access loop classes, and EP TCP endpoint is connected to LR live ref. LR live ref is connected to USR unicast server ref. USR unicast server ref is connected to unicast remote object, and then it's going through here and it's connected to unicast remote object is connected to RMI object here. Now you can see an expense reporting architecture in server defined policy. This figure shows the general picture of such a dynamically configurable expense reporting system. Client displays a GUI graphical user interface to a user who fills the fields of the expense report. Clients communicate with the server using RMI. Server stores the expense reports in a database using JDBC, the relational database package. So far this may look like any multi-tier system, but there's an important difference. RMI can download behavior. Suppose that the company policies about expense reports change. For example, today the company requires receipts only for expense over $20. Tomorrow the company decide this is too lenient. It wants receipt for everything except for meals that cost less than $20. Without the ability to download the behavior, you have the following alternatives when designing your system for change. Install the policy with the client. When the policy changes, this requires updating all clients that contain the policy. You could reduce the problems by installing a client on a handful server machines and requesting all users to run the client from those servers. This would not completely solve the problem. Anyone who leaves the program up and running for days would not be updated, and there are always some people who copy the software to a local disk for efficiency. Point 2, next point, you could have policy checked by the server when each entry is added to the expense report. This would result a lot of traffic between client and server, clogging network and burning the server. This would make a system more fragile. A network failure would hold people in their tracks instead of only affecting them when they actually submit an expense report or start a new one. It would also mean that adding an entry would be slow, since it would require a round trip across the network to the burdened server. Next point is, you could have a policy checked by the server when report is submitted. This lets the user create a lot of bad entries which must then be reported in a batch instead of catching the first error immediately, giving the user a chance to stop making the error. Users need immediate feedback on errors to avoid wasted time. With RMI, you can have the client upload behavior from the server with a simple method invocation, providing a flexible way to offload computation from server to clients while providing users with faster feedback. When a user is ready to write up a new expense report, the clients ask the server for an object that embodies the current policies for expense report as expressed via a policy interface written in Java. The object can implement the policy in any way. If this is the first time that client's RMI runtime has seen this particular implementation of policy, RMI will ask server for a copy of the implementation. Should the implementation change tomorrow, a new kind of policy object will be returned to the client, and the RMI runtime will then ask for that new implementation. This means that the policy is always dynamic. You can change the policy by simply writing a new implementation of general policy interface, installing it on the server, and configuring server to return object of this new type. From that point on, any new expense report will be checked against the new policy by every client. This is a better approach than any static approach, because all clients do not need to be halted and updated with new software. Software is updated on the fly as needed. Server is not burdened with entry checking that can be done locally. Next point, allow dynamic constraint, because object implements, not just data, are passed between client and server. Next point, lets user know immediately about errors. Here you can see a server interacts with clients via RMI. When clients interact with server via RMI, server interacts with expense record via JDBC here. Here you can see architecture, basically stub and skeleton. The RMI system is designed to provide direct, simple foundation for distributed object-oriented computing. Architecture is designed to allow for future expansion of server and reference types so that RMI can add features in a coherent way. When a server is exported, its reference type is defined. In the examples here previously discussed, we exported the servers as unicast remote object servers, which are the point-to-point unreplicated servers. The reference for those objects are appropriate for this type of server. Different server types would have different reference semantics. For example, a multicast object would have reference semantics that allow for replicated service. With client, when client receive a reference to a server, RMI downloads the stubs that translate calls on a reference into remote calls to the server. As shown in this figure, the stub marshals the arguments to the method using object serialization, then send the marshaled invocation across the wire to the server. Server side, the call is received by the RMI system and connected to skeleton. Which is responsible for unmarshalling the argument and invoking server implementation of the method. When server implementation completes, either by returning a value or throwing an exception, the skeleton marshals the marshals the result and send the reply to the client stub. The stub unmarshals the reply and either returns the value or throws an exception as appropriate. Stubs and skeletons are generated from the server implementation, usually using the program RMIC. Stubs use references to talk to skeleton. This architecture allows the reference to define the behavior of communication. The references used for unicast remote object servers communicate with a single server object running on a particular host or pod. With stub reference separation, RMI will be able to add new reference type. A reference that dealt with replicated servers would multicast server requests to an appropriate set of replicants, gather in responses and return an appropriate result based on those multiple responses. Another reference type could activate the server if it was not already running in a virtual machine. The client would work transparently with any of these reference types. Here you can see, for example, exp server.get policy method as an example. Then in the stub, it's go through marshal parameters and request. Then it's moved to skeleton, unmarshal parameters, invoke implementation, it's moved to implementation, then return new today's policy, for example. Then it's moved back to skeleton and receive return O exception, marshal return No exception, then send reply, then it's back to skeleton stub and unmarshal reply and return value throw exception. Here you can see the RMI in an evolving enterprise. You can use RMI today to connect new Java applications or applets and existing servers. When you do this, you allow your organization to benefit incrementally from expanded Java use over time. When parts of your system are rewritten in Java, RMI allows the benefits of Java to flow from the existing component into new Java code. Consider the path of a single request in a two-tier system from the client to server and back again. Using RMI means that you can get the benefits throughout your system. By using RMI as transport between client and server. Even if the server remains in non-Java code for some time, if you choose to rewrite some or all of your servers in Java, you will get leverage from your existing Java components. Some of most important Java advantages you maintain are the object-oriented code use, the ability to pass object from client to server and server to client, means that you can use design patterns and other object-oriented programming techniques to enhance code reuse in your organization. Passing behavior, next point, passing behavior. The object passed between client and server can be of types not previously seen by other side. Implementation will be downloaded to execute new behavior. Next point, type safety. Java objects are always type safe, preventing bugs that would occur if programmer makes a mistake about the type of an object. Security. Java classes can be run in a secure fashion, allowing you to interact with client that may be running in an untrusted environment. Here is that diagram showing a client written in Java using RMI to talk to the server. The request the request arrow has been shaded to show where you get the Java safely, object-oriented and other advantages. A small amount of Java code connects to a legacy wrapper that uses existing server API. The legacy wrapper is a bridge between Java and existing API, as shown in this in the implementation of, for example, get unpaid and shut down as an example. In this diagram we show it written using JNI, but as shown in the other legacy wrapper could use JDBC, or when it is available, Twin Peaks. Contrast this diagram with one in which a language neutral system using an interface definition language, commonly called an IDL, introduces a least common denominator connection between the client and the server. A legacy wrapper must still be written to connect the IDL defined calls to the existing server API. But with an IDL based approach, the benefits of Java has been isolated on the client side, because the client's Java is reduced to least common denominator before crossing the server. Suppose you decide that rewriting some of the server in the Java would be useful for you. This might be for any reason, such as wanting the improved reliability of safe Java system, or because you want to reduce porting cost, or possibly the vendor from whom you bought some of your server implementation has provided an upgrade that takes advantage of Java. Here is how RMI based picture now look like. More of the requests now benefit from having Java. The objects that you pass across the wire between client and the server can now have more benefit to overall system. You could, for example, start passing behavior across the same remote. Now you could, for example, start passing behavior across the same remote interface you already have defined to enhance the value of client and server. Compare this to the ideal approach. You would have achieved benefits of Java that are local to the server, but you cannot leverage expanded value of Java for the client server connection. The benefits of Java are cut off at the ideal boundary. Because ideal cannot assume that Java is on the other side of the connection. You cannot get the full benefits of Java in your system without throwing out the ideal work and rewriting it using RMI. This lost opportunity becomes greater as you use Java in more of your enterprise. Using RMI, you get benefits of Java all the way through the system. Using ideal approach, rewriting the server in still only gives you localized benefit isolated to the server alone. You can use RMI today to connect your servers without rewriting it in Java. RMI is simple to use, so it's easy to create the server-side RMI class. The legacy wrapper is of similar complexity in either base. If you use the ideal based distribution system, you will create isolated pockets of Java that share no benefits with each other. RMI lets you connect easily now, and as you decide to expand your use of Java, you will get expanded benefits from synergy of having Java on both sides of the wire. Here you can see a client and server. The request is going like this, and here you can see a client is connected to server. Here client interacts with server. Here you can see client and server. Here Java interacts with JNI, a legacy wrapper. JNI interacts with non-Java here in JNI, and non-Java is inside server. Requests moving like this. Here client Java and ideal is in client side, and ideal legacy wrapper and non-Java is in server side. Ideal is in both client and server here. Java is interacts with ideal interacts with legacy wrapper interacts with non-Java. Request is like this here, and here Java is in client and server. Java interacts with JNI interacts with non-Java. JNI is legacy wrapper here, and Java, JNI and non-Java is in server side here. Request move like this, and here ideal is in client and server side. Java and ideal is in client side. Ideal and Java, JNI and non-Java are in server side. Java in client side interacts with ideal interacts with Java in server side. Java in server side interacts with JNI interacts with non-Java. JNI is here legacy wrapper. Request move like this. Here Java is in both client and server side. Request move like this. Here Java is in client side, and ideal is in client and server, and here Java is in server side. Java in client side interacts with ideal. ideal interacts with Java in server side. Request move like this. Now we are considering how Java RMI works. This diagram illustrates the process of setting up and accessing a remote object. The Java RMI remote method invocation can be used to invoke methods of objects in other Java virtual machines. JVM. The JVM can be on the local host or another host. RMI allows the client, the thread that actually invokes a method in the remote object, to invoke a remote method on a server. The thread that contains the remote object, as if the remote object were contained on a client host from the programmer's perspective. What really happens is that when the client calls the method in a remote object, instead of letting the Java runtime take care of the call as it would for regular Java object, RMI runtime system takes over the routes, the calls over the network to remote object. In essence, the RMI runtime opens a socket connection on an anonymous port to the remote object running on the server host. The RMI runtime running as part of the JVM on the server side listens on this special port for incoming RMI request and invokes the requested method on the server side when one is received. Information received returned by the called method is passed back to the client through the socket after the socket is closed. None of the underlying communication is visible to the programmer. As a programmer, you may wish to access the remote object from one or more servers out on the network. The remote object could, for example, contains method which, when invoked, return information about the hardware or software running on the server. Sound familiar? These remote agent objects may exist on many servers on the network. Here, server refers to the network element which contains remote object whose methods can be accessed by the interested client using RMI. So how does a client, which may come into existence at any time, find out what remote objects can access on the server on the network? The answer is by getting the server object reference from the remote object registry. Remote objects registry run on a server where the remote object exists. It contains a list of references to all remote objects on that server that are accessible to clients through RMI. A client may query the remote object registry, here henceforth known as the registry, to obtain a reference to a remote object, and sets a local object reference to that remote object. For example, if the object obj was defined in the Java client program, the registry could be queried by specifying the URL of the remote object to find the reference to the object remote obj, and obj could be set up to point to remote obj. The calls to methods obj would be intercepted by the RMI runtime and redirected to remote obj on the server using socket communication as explained previously. Note that both obj and remote obj must be instances of the same class, or more specifically, obj must implement the interface of the class that remote obj is instantiated from. More on this instantiated from. This explains how to access remote method from a client. But how does one set up method on a server so that they can be accessed remotely? Each remote object server hosts the computer must be running the registry. The registry may be running in the same JVM as remote object or in a separate JVM. The registry is an anonymous Java thread that responds to requests from other Java programs on the network using socket communication. The registry listens to port 1099 by default for incoming requests. This port can be changed, but all clients will have to be updated accordingly. This way you could have more than one registry running on the same server, necessity if the registry is built in to more than one remote object on the server. Before any object become remotely accessible to clients, they must be registered in the registry, a process called binding. Objects may only be bound to the registry on the same host. In this means that you will never need to have registry running on a client that is not making any of its object remotely accessible. If there are many servers on the network offering remote object, then there will be also many registries that the client may choose to remote object from. The registry need only be accessed first time that the remote object is defined on the client. To use the previous example, when obj is instantiated and make a point to remote obj, the act of making it point to remote obj involves the registry query. Subsequent method calls to obj are handled by RMI runtime on the client. So registry is only used for bootstrapping, that is setting up access to the remote object for the first time. Because there can be more than one registry running on a host, and there may be many hosts serving remote objects on the network. There must be a mechanism for finding bound remote object for various registries. The local registry class contains static method that return a reference to a registry on the current host. Current host at specified port, a specified host or at a particular port and a specified host. Using this information, the bound remote objects on the registry can be listed, or a reference can be obtained for setting up a client object to access method in a remote object. This diagram will illustrate the process of setting up and accessing the remote object. Here, remote objects, step 1, remote objects is connected to remote object registry via bind serve object reference in remote object registry. Step 2, here client is connected to remote object registry via get server object reference from registry. Step 3, here client is connected to remote object via invokes method in the remote objects as if they were local to the client. Here client is inside JVM, which is in the client host, and here remote object is inside the JVM, which is in the server, and here remote object registry is in a separate JVM in a server host. Here you can see how communication and process take place in RMI. Here you can see RMI registry has interactions here. you can see client procedure, local call, and remote reference are in one section, and server procedure, server stub, and remote reference are in the other section. And remote reference, the argument results are communicated to the two sections here. Communication can be downward here or upward here. Here you can see Java RMI architecture in a different view. Java RMI is designed to simplify the communication between two objects in a different virtual machines by allowing an object to object in an object to invoke the methods of an object in another virtual machine in the same way as methods on local objects invoke. To invoke methods on a remote object, remote reference to that object has to be obtained, since the object resides in the different virtual machine and hence in a different namespace. The registry is used to manage remote references. RMI servers can register their objects in a registry, after which clients can obtain a reference to those remote objects. The general architecture of RMI is shown in this figure. The first server creates a remote object and registered it at the registry, which is shown by arrows 1 here in the figure. The client can obtain references to object stored in the registry, as shown in the arrow 2 here, in the arrows here. When the client invokes a method on a remote object, the method is actually invoked, shown by arrow 3 here, on a stub object located in the same JVM as the client's JVM. The stub object makes a message containing a name of the method together with the parameters called marshalling, and send this message, shown by arrow 4, to the associated skeleton object residing in the server's JVM. The skeleton object extracts the method name and parameters from the message called unmarshalling, and invokes the appropriate method on the remote object with which it is associated, shown by arrow 5 here. Remote objects executes the method and passes the return value back to the skeleton, arrow 6 here. The skeleton in turn marshals the return value in the message and sends this message to stub object, arrow 7. The stub unmarshals the return value from the message and returns this value to the client program, arrow 8. The methods of a remote object can be invoked remotely must be specified an interface that extend the RMI defined remote interface. Every method in the interface must be declared to throw the remote exception in order to account for errors during remote method invocation. A number of subclasses of remote exception are defined that represent the various errors that can occur. A remote object typically declared to implement at least one remote interface and also extend the remote server class or one of its subclasses. After creating a remote object, it needs to be exported, which makes it available for remote access. Once created and exported, the remote object must be registered with the registry by invoking either bind or rebind method of the naming class, providing them with the remote object and an appropriate name. The remote interface of the remote object is used as the type of the remote reference on the client side. A remote reference can be obtained by invoking lookup method of the naming class, providing the name of the desired remote object. When invoking a method through the remote interface, remote exception must be caused to handle the errors during the remote method invocation. Exceptions that occur during the actual execution of the remote method at the server are known to the client. Server are thrown to the client encapsulated in a server runtime exception object. Other exceptions occurring at the server are encapsulated in a server exception object. After writing and compiling a remote interface and the remote object implementation, the RMI stub skeleton compiler RMIC can be used to generate stub and skeleton pair for accessing the remote object. The stub and skeleton, and thus the entire communication is completely shielded from the programmer. Here you can see a client host and here server host. Client object and stubs are inside the client host. Registry, server, remote object and skeleton are inside the server host. Here step 1, registry interact with the remote object and server interact with registry and remote object here. Here registry interacts with the client object, and here 3 client object is connected to stub. 4 stub is connected to skeleton. Skeleton is connected to remote object. The remote object is connected to skeleton. Skeleton is connected to stub. Stub is connected to client object. Here you can see remote method, Java remote method invocation, RMI architecture in different view here. Java remote method invocation RMI, it gives a way for Java program on a machine to interact with object residing in different JVMs. To import the important blocks of the RMI architecture are the stub class, skeleton class, and object serialization. RMI needs a layered architecture where each of the layers may be enhanced without affecting the other layers. The layers may be defined as given here: application layer, server and client program, server and client program, skeleton and stub layer, intercept method invoke made by the client and redirect these calls to a remote RMI service. Remote reference layer sets up connections to remote address spaces, understands and manages connections, how to manage and interpret references given from clients to the remote servlet, remote service objects. Transport layer based on TCP/IP connections between operating systems in a network. It gives basic connectivity as well as some firewall penetration goals. RMI stub classes give a reference to skeleton object located in the different address space on the different or same machine. That is a typical example of a proxy design pattern. which builds an object executing on another JVM seems like a local object. In JDK 5.0 and later the RMI facility access dynamic proxies instead of generated stubs, which builds the RMI easier to use. Here you can see a client and server. Clients interacts with server. Here you can see a client object, stub and remote reference manager inside this client process, and RMI registry, remote object, skeleton and remote reference manager in server process. Here load stubs, one load stub, RMI registry or JNDI server. Here two client objects are connected to RMI registry via lookup stub. Here RMI registry is connected to client objects via return stub, and here stub is connected to skeleton via method call on a remote server objects, and skeleton is connected to stub via send results or exceptions. Here the stub is here client object interacts with stub. Stub interacts with remote reference manager. Remote reference manager interacts with interacts to the reference manager in server process via RMI transport layer. Remote reference manager in server process here can be seen here. It interacts with skeleton. Skeleton interacts with remote objects. Here step 4 and 5 are logical explanations only. Neither stubs nor skeletons use sockets directly. Here the actual calls are made through the remote reference manager. The remote reference manager handles the actual details of communicating with remote processes. This extra layer manages network communication and conserves scarce resource like sockets. Here the example here, program 1 and program 2. Program 1 stub is connected to skeleton in program 2, and program 2 stub is connected to skeleton in program 1, as an example. Here you can see a remote method invocation, and here you can see remote procedure call. Working in architecture of RPC, here RPC is analogous to a function call extending a notion of conventional local procedure calling, so that the procedure need not exist in the same address space as the calling procedure. Like a function call, the calling argument are passed to the remote procedure, and the caller wait for the response to be returned from the remote procedure. The client makes a procedure call and send the request to the server. As shown in this figure, the thread is blocked from processing until either a reply is received or it times out. When the request arrived, the server calls the dispatch routine that performs the request service and send the reply back to the client. After RPC call is completed, the client program continues its normal execution. Stubs are generated at static compilation time and then deployed to the client side, which is used as a proxy for client. Client side proxy acts as a mediator between the client and the broker and provides additional transparency between them and client so that the remote object appears like a local one. Proxy hides the inter-process communication IPC at the protocol level and perform marshalling of parameter values and unmarshalling of results from the server. Skeleton is generated by the service interface compilation and then deployed in the server side, which is used as a proxy for the server. Server-side proxy encapsulate low-level system-specific networking functions and provides high-level APIs to mediate between server and the broker. It receives the request, unpacks the request, unmarshals the method arguments and calls the suitable service, and then marshals the results before sending it back to the client. The sequence of events during RPC, the client calls the client stub. The call is a local procedure call with parameters pushed on to stack in the normal way. Client stub packs the parameters into a message and make the system call to send the message. Packing parameters is called marshalling. Client local operating system send the message from client machine to the server machine. Local operating system on the server machine passes the incoming packet to the server stub. The server stub unpacks the parameters from the message. Unpacking the parameters is called unmarshalling. Finally, service stub calls the server procedure. The reply traces the same steps in the reverse direction. Here you can see remote method invocation. Remote method invocation is a technology introduced by Java that allows invocation methods that are remotely located by simply calling them using desired interfaces. RMI technology allows us to distribute over business logic. That is making business logic available on a remote server, letting it to access to clients. RMI is often called RPC with object orientation. That is RPC but with ability to pass one or more object along with the request. Object can include the information that will change the service that is performed on the remote computer as delineated in this figure. For example, when a user at the remote computer fills out an expense account, the Java program interact with the user could communicate using RMI with the Java program in another computer that always had the latest policy about expense reporting. In reply, the program would send back an object and associated method information that would enable remote computer program to screen the user expense account data in a way that was consistent with the latest policy. User and company both would have the same would save time by catching mistakes early. Whenever the company policy changed, that would require a change to the program only one computer. RMI is implemented as 3 layers. Stub and skeleton layer. The stub program represents the remote object, and also acts as a gateway to corresponding skeleton at the server end. And the stub appears to calling program to be the program being called for the service. Remote reference layer. This can behave differently depending on the parameters passed by the calling program. For example, this layer can determine whether the request is to call a single remote service or multiple remote programs as in multicast. Transport connection layer. This setups and manages the request. A single request travels down through the layers on the one computer and up through the layers at the other end. RMI registry is a central repository keeping a track of all services being exposed from the current network. Since all client requests for services through the RMI registry, the location of the application or service is unknown to the clients, hence making the application location neutral. Here you can see in the remote procedure call here, this is the computer A client and computer B server. Client program, marshalling, client program, stub and OS hardware are inside computer A client. Client program, skeleton and OS hardware here are inside computer B server. Here the client program calling procedure is connected to marshalling, and marshalling and unmarshalling are inside the stub here. Client program, the calling procedure is connected to marshalling through arguments. Marshalling is connected to OS hardware, client network routings and interface. OS hardware, client network routings and interface in computer A client is connected to OS hardware, client network routings interface in computer B server via marshaled return. OS hardware is connected to unmarshalling in skeleton. Unmarshalling is connected to client program call procedure via arguments. Client program is connected to marshalling via return. Marshalling is inside skeleton, and marshalling is connected to OS hardware. OS hardware is connected to OS hardware in computer A client via marshaled arguments. OS hardware is connected to unmarshalling in stub. Unmarshalling is connected to client program calling procedure via return. Here you can see the remote method invocation. Here you can see client host and server host. Server object interface, client program and server stub are inside client host. Server object interface, service skeleton and server object are inside server host, and RMI registry is inside RMI host. Here you can see one server object is connected to RMI registry via register server object naming.rebind. Here in step 2, client program is connected to RMI registry host via look for server object naming.lookup. And here step 3, RMI registry host is connected to client program via return service stub. Here step 4, data communication from service stub, remote reference to remote reference layer, and here server host is connected to remote reference layer here. And here you can see server object is connected to RMI registry host, and client program is connected to RMI registry host. RMI registry host is connected to client program via return service stub, and client program interact with service stub. Service stub is connected to remote reference layer. Remote reference layer interacts with transport connection layer. Transport layer connection layer interacts with network layer, and network layer interacts with transport connection layer. Transport connection layer interacts with remote reference layer, and server host is connected to remote reference layer. Service skeleton interacts with server object, and server object is connected to registry, RMI registry host. Here you can see event flow in RMI. Here you can see the event flow in RPC. Here you can see server. Here you can see machine A, network, and machine B. Client program here is connected to machine B via call RPC method. Call RPC, and then it invokes service. Then it's move to call service, and service execute, then return answer, and request in machine B, then request completed. Then machine B is connected to machine A via return and answer, and the program then program continues with this is our remote method invocation. Here the RMI registry, see the called object is connected to, here calling object is stub, RMI registry, listening skeleton, and called object. Here called object is connected to RMI registry via bind, and RMI registry is connected to bind to called object via bind OK. And here calling object is connected to remote registry via lookup, and RMI registry via lookup, and RMI registry is connected to calling object via address. And here, for example, hello is the calling object is connected to called object via hello here, for example, and called object is connected to calling object via hello return value here, for example. Here you can see in the logical operation the semantic overview of different actors passing your RMI request along. Here you can see client and server. In client side, server IMPL stub is there, and server side server IMPL skeleton and server IMPL object are there. Here you can see a control flow here, and here wait is connected to server IMPL stub, and server IMPL stub interacts with server IMPL skeleton, and server IMPL skeleton interacts with server IMPL object. Here server IMPL stub is connected to server IMPL skeleton, and server IMPL skeleton is connected to server IMPL object, and server IMPL object is connected to server IMPL skeleton, and server IMPL skeleton is connected to server IMPL stub, and server IMPL stub is moved to continue in control flow. Here you can see the in the logical operations, the logical operation of RMI call. The client waits until the server returns. Java processes can communicate by calling Java RMI. Communication happens solely between Java virtual machines, thereby using interpreted bytecode which can run on different machines. Java RMI communication goes from from a client process towards the server object. The client requests the name of a certain object at a certain registry. Normally it received a stub object in response. The client requests the name of the certain object at the central registry. Normally it receives the stub object in response. Every call invoked upon this stub object on a client will be translated by RMI architecture to a call on the matching server object on the server. As long as the server doesn't send a response, that client keep on waiting. This is illustrated in this figure. The protocol between client and server is defined as an interface extending the remote type. This is compatible with IDLs in COBA. In this instance, however, it's a language feature that and does not require a special compiler. This interface, the protocol description is only class file that out to be shared between client and server. Client uses this information to create stubs. The server uses this information to create skeleton listening. Here you can see a calling object is stub, RMI registry, listening is skeleton, called object. Here called object is connected to RMI registry via bind, and RMI registry is connected to called object via bind OK. Here calling object is connected to RMI registry via lookup, and RMI registry is connected to calling object via via address, and here calling object then is connected to called object via hello, and here called object is connected to calling object via hello return value. Here you can see internal operation. Here remote object calling in Java RMI. Some serialization and deserialization interface to Java helps exporting an object and all the object it knows and depends on to a byte stream. The standard behavior for serialization is to serialize the object and all the objects it contains. If we want to modify this behavior, we can use the externalizable interface which describes how the object is to be exported. To be able to contact a remote object as if it were a local object, one should create stubs for all the remote objects which will be contacted. One can do this automatically at compile time using RMI. Such a stub will provide all the methods the remote object supports, and fill in the bodies with the code to contact the remote object. The logic within one such a stub body is quite simple. One, contact the remote object by object using sockets. Serialize all the argument passed to the stub by the caller. Send out all the arguments and wait for the answer, which will be the result. Receive and read the result, deserialize the result, and 7 return the result to the original caller. The object that is being exported at the server side should offer a way to be contacted by the remote clients. This is done by skeleton, which contains some listen code and logic to contact the actual exported object. The logic in a skeleton is also very simple. One, listen to the connections and to accept an incoming connection in a separate thread. 3, receive the serialized argument. For deserialized, this is received serialized argument, and for deserialized the arguments, 5, invoked method call upon the correct object. 6, serialize the result of invocation. 7, send back the result over the socket. This figure illustrates how we can transparently contact a remote object. We see how setup when we want to contact a client from within the server, the client need to export an interface and become a listening server itself. Here you can see object, calling object, stub, RMI registry, server thread, listening skeleton, and called object. Here listening skeleton is connected to called object here, and here called object is connected to our RMI registry via bind, and RMI registry is connected to then called object via bind. Okay, and then calling object is connected to RMI registry via lookup, then RMI registry is connected to calling object via address. Then here, for example, hello method is called, and here serialize occurs, and then its stub is connected to listening skeleton via send method, and accept method is there, and then listening skeleton is connected to server thread, and then read method and deserialize method, and then server thread is connected to called object. Here this is, for example, hello method, and here called object is connected to server thread, then deserialized method, then server thread is connected to stub via send method, and received method is called, then deserialized method, then stub is connected to calling object via calling object. Now we are considering Java threads. In this diagram, the full lines indicates a running process. Dotted line indicates a waiting listening process, and horizontal dash line indicates wait and return. In this figure, we see how a new thread is spawned every time call comes in. Here you can see the algorithm here, a distributed recursive factorial here. In all its aspect, Java is an innovating language. For example, it introduces garbage collection in the industry, and on another note, we see how Java introduces a standard threading library. Compare this with C, which has all kind of dirty libraries and tricks like set jump, set JMP, and long JMP to solve multiple sessions. A thread is execution context which can run together with other threads in the same environment. The difference with processors is that threads do share memory, while processors don't share memory. This is important because Java RMI has already seen wait before returning an answer. With Java RMI, client can ask the server to execute a method and return an answer in the meantime, the client simply wait and now let's have a look at the Java programming algorithm here. The fact app here class exports the fact_cals interface. The fact_cals is an object that is able to calculate factorial of a certain number by multiplying that number by factorial of that number minus 1. To do this last step, the fact_cals needs to be supplied another fact_cals. This can be seen in the definition of fact method. When we start this application, it will first try to look up an existing fact_cals. If there is one, it will contact that fact_cals to calculate some factorial. If there's none, it will become a fact_cals itself and announce it in the registry. To start this program, first the RMI registry should be started, and afterward two times the fact app, two times the fact app. The last fact app the fact_cals 2 from now on request fact_cals 1 to calculate the factorial of 3. In return, fact_cals 1 will request the fact_cals 2 here to calculate the factorial of 1. But how it is possible? How can the original request be uninterrupted while he is still waiting? The answer lies in the Java threading mechanism. Every time an RMI call comes in, server thread will spawn a new thread which handles the request. This can be seen in figure here. Here you can see fact_cals 1 here, RMI registry, and fact_cals 2 here. Fact_cals 1 is connected to RMI registry through lookup, and RMI registry is connected to fact_cals 1 through not bound, and then fact_cals 1 is connected to RMI registry via bind, and RMI registry is connected to fact_cals 1 by bind OK. Then fact_cals 2 is connected to RMI registry via lookup, and RMI registry is connected to fact_cals 2 address, and then this is in a server skeleton area here. Fact_cals 2 is connected to called the fact3 accelerator 2, and then it came back to fact2 accelerator 1, fact_cals 1. Then it came back to fact1 fact_cals 2. Then it back to fact_cals 0 fact0 fact_cals 1, and then 1 here, then 2 and 6, and then the fact_cals 2 here. Now we are considering Java RMI workflow. Here's how a typical RMI invocation usually work. One server registers service from RMI and bind its address. To client registers service from RMI and obtain the target address. 3. Client invokes methods of local stub object in the same way of invoking other local objects. 4. Local stub object ships invoking information and send it to the server via network. Skeleton object 5. Skeleton object of the server receives the network request and unships the information. 6. Server runs invocation on the target object. Based on the information and returns the shipped results back to the client via network. Here you can see remote object implementation and remote interface here, and here server registered, server is connected to registry via bind, and here client application is connected to register via lookup, and registry is connected to client application via remote reference. Here client application is connected to stub via fargs here, and stub is connected to skeleton and via Marshall stream, and skeleton is connected to so via connected to here via fargs, and it returns returns to skeleton, and skeleton is connected to stub, and stub is connected to client application via return or exception. Here you can see invocation lifecycle. Here you can see client code and stub in the client, and so RMI object and skeleton in the server, and here network, and here one client code is connected to stub via invoke method via stub, and stub is connected to network via serialize arguments transmit. Here network 3 network is connected to skeleton via receive deserializes arguments, and here skeleton is connected to RMI. 4 skeleton is connected to RMI object via call actual method with args. Here step 5 RMI object is connected to skeleton via returns response or exception. Here skeleton is 6 skeleton is connected to network via serializes response transmit. Here step 7 network is connected to stub via receives deserializes response. Here step 8 stub is connected to client code via returns response. Here now we are focusing on client program. A typical client program obtains a remote reference to one or more remote objects on a server and then invokes methods on them. Here you can see Java RMI architecture in a different diagram. Java remote method invocation RMI allows the distribution of Java objects, enabling clients to invoke methods on remote objects. Here in step 1, a server exposes a remote object by exporting its client stub to the RMI registry. In step 2, clients use the registry to look up exported objects and receive their stub. Step 3 here, if the client JVM does not find the class definition of the remote objects interface or any other types that are used within the interface in its local class path. It queries the code base whose location can be provided within the stub by the remote object server. Step 4, client can use the client can then invoke methods on the remote server objects. The standard RMI registry requires the remote server object and the RMI registry to be collocated on the same machine. For clients to be able to contact the registry, this machine must be publicly reachable. The same applies to the code base, which must reside on a publicly reachable HTTP server. I repeat the process. Here the server registers the remote object, step 1, and in step 2 the client looks up the stub in the registry, and step 3 the client requests the stub class file here, and the client invokes method on the remote object, and the remote object and the registry have to reside on the same machine. Here you can see a remote object, registry, code base, and client. Here remote object rebind registry, and here client looks up registry and stub is returned from registry to client, and clients get code base and class is returned from code base to client. Client invokes remote object and results are returned from client to remote objects to client. Here we are considering how do Java RMI clients contact remote Java RMI servers. For an RMI client to contact a remote Java RMI server, the client must first hold the reference to the server. The naming.lookup method call is the most common mechanism by which client initially obtain references to the remote servers. Remote references may be obtained by other means. For example, all remote method calls can return remote references. This is what naming.lookup does. It uses a well-known stub to make a remote method call to the RMI registry, which send back the remote reference to the object requested by the lookup method. Every remote reference contains a server hostname and port number, which allows a client to relocate the VM that is serving a particular remote object. Once a Java RMI client has a remote reference, the client will use the hostname and port provided in the reference to open a socket connection to the remote server. Please note that with Java RMI, the terms client and server can refer to the same program. A Java program that acts as a client RMI server contains exported remote object. A Java RMI client is a program that invokes one or more methods on a remote object in other virtual machine. If a VM performs both of these functions, it may be referred to as an RMI client and a Java RMI server. Here you can see RMI client, and here you can see RMI registry. Here my interface mi and mi equal my interface naming.lookup the server / object to get. Naming lookup is inside RMI client, and step 2, create new instance of well-known stub class for the RMI registry running on the server. Step 2, call lookup object to get on the registry using the reference created in step 2, and this is connected to RMI registry. And registry return, step 4, the registry returns a remote reference to object to get. And step 5 is from naming.lookup. Naming.lookup returns the remote reference to object to get to the RMI client. Here you can see an RMI distributed applications that uses the RMI registry to obtain a reference to a remote object. RMI application often comprise two separate programs, a server and a client. A typical server program creates some remote objects, makes reference to these objects accessible, and waits for client to invoke methods on these objects. A typical client program obtains a remote reference to one or more remote objects on a server and then invokes method on them. RMI provide mechanism by which the server and the client communicate and pass information back and forth. Such application sometimes referred as a distributed object application. Distributed object applications need to do the following: locate remote objects. Application can use various mechanisms to obtain references to remote objects. For example, an application can register its remote objects with RMI simple naming facility, the RMI registry. Alternatively, an application can pass and return remote object references as a part of remote invocations. Communicate with remote objects. Details of communication between remote objects are handled by RMI. To the programmer, remote communications look similar to regular Java method invocations. Load class definitions for objects that are passed around. Because RMI enables object to be passed back and forth, It provides mechanism for loading and object class definitions as well as for transforming an object's data. This diagram this illustration depicts an RMI distributed application that uses RMI registry to obtain a reference to a remote object. The server calls the registry to associate or bind a name with a remote object. The clients looks up the remote object by its name in the server's registry and then invokes a method on it. This illustration also shows that the RMI system uses an existing web server to load class definitions from server to client and from client to server for object when needed. Here RMI client is connected to RMI registry. So RMI is passed from RMI client to RMI registry. RMI client is connected to RMI server. RMI is passed from RMI client to RMI server, and RMI server is connected to RMI registry, and RMI is passed from RMI server to RMI registry. RMI registry is connected to remote server. URL protocol is passed from RMI registry to remote web server. And RMI client is connected to web server, and URL protocol is passed from RMI client to web server. RMI server is connected to web server. URL protocol is passed from RMI server to RMI web server. Here you can see a remote method invocation. Here the all method published on server are registered on RMI registry like UDDI for web services. The client calls the local method stub to perform this operation. The stub on the client calls RMI registry to know whether that method exists. And correct way to call it. Client stub calls this method on the server skeleton. Calls this method on server. So skeleton receive this request and communicate with the software on the server. Then it receives the response and send this response to the client stub. Here you can see a client host here. and server host here. Server object interface, client skeleton, and server objects are in client server host. And here step on the server object registers server objects on RMI registry host. RMI registry is in RMI registry host. And step 2 here, look, then here the server object interface, client program, and service stubs are in client host. This is client program. And here server client program looks for server objects in RMI registry host. RMI registry host return server stub here to client program. Client program interact with server stub, server stub do the data communication between with service skeleton, and service skeleton interacts with server objects. And simply server objects register server object with RMI registry here, RMI registry host here, and client program looks for server object in RMI registry host, and RMI registry host return server stub to our client program, and data communication then occurs between server stub and server skeleton here. This is the another diagram for RMI architecture here. Java remote method invocation RMI, which is a simple and powerful network object transport mechanism, provides a way for Java program on one machine to communicate with objects residing on different address spaces. RMI is an implementation of the distributed object programming model comparable with COBA, but simpler and specialized to the Java language. The overview of RMI architecture is shown in this figure here. This is another figure to depict RMI architecture. The important parts of the RMI architecture are the stub class, the object serialization, and the server-side runtime system here. The stub class implements the remote interface and is responsible for marshalling and unmarshalling the data and managing the network connections to the server. The instance of a stub class is needed on each client. Local method invocations on stub class will be made whenever a client invokes a method on the remote objects. Java has general mechanism for converting objects into streams of bytes that can later be read back into an arbitrary JVM. This mechanism is called object serialization is essential functionality needed by Java RMI implementation. It provides a standardized way to encode all information into a byte stream suitable for streaming to some type of network or a file system. In order to provide functionality to an object, must implement the serializable interface. A server-side runtime system is responsible for listening for invocation request on a suitable IP port and dispatching them to the proper remote object on the server. Since RMI is designed for a web-based client-server application over slow network, it is not clear it is suitable for high-performance distributed computing environment with low latency and high bandwidth. A better serialization would be needed since Java's current object serialization often take at least 25% and up to 50% of time needed for remote invocation. Here you can see client and client code and stub are inside the client, and you can see the server here. RMI runtime system and remote objects are inside server. Here client code calls stub method locally, and stub sends Marshall's arguments. RMI runtime system call remote object method locally to remote object, and remote object returns value or throw exception to RMI runtime system, and RMI runtime system sends Marshall result or exception to stub, and stub returns value or throw exception to client code. Here we are considering compile an example. These instructions assume development is in the Zelda home directory. The server program is compiled in the home directory for user Zelda, but copied to the public _HTML directory for user Zelda where it runs. Here is the command sequence for Unix and Win32 platforms, and explanations as follows. The first two Java C commands compile remote server and send class and interface, and the third Java C command compiles the RMI client 2. The last Java C command compiles the RMI client 1. Next line runs the RMI C command on the remote server class. This command produces output class of the form class class name underscore stub.class and class name underscore scale.class. These output classes let client invokes method on the remote server object. First copy command moves the remote server class file with its associated scale and stub class files to publicly accessible location on the home Zelda public _HTML classes directory, which is on the server machine. So they can publicly accessed and downloaded. They are placed in the public _HTML directory to be under the web server running on server machine, because these files are accessed by client program using URLs. The second copy command moves the send class file to the same location for same reason. RMI client 1 and RMI client 2 class files files are not made publicly accessible. They communicate from their client machines using URLs to access and download the remote object files in the public_HTML directory. The RMI client 1 is invoked from the client-side directory that uses the client-side web server, server-side web server and client-side Java VM to download the publicly accessible files. And RMI client 2 is invoked from the client-side directory and uses the server-side web server and client-side Java VM to download the publicly accessible files. So here you can see remote client 1 is inside client host, client side Java VM, remote client 2 is in client host, client side Java VM here, and remote server object is in server host, the server side web server and Java VM. RMI client 1 RMI client 1 interacts with server host and RMI client 2 interacts with server host. Here you can see a code segment to implement the client. The client program obtains a stub for the registry on the server host, lookups the remote object stub by name in the registry, and then invokes say hello method on the remote object using stub. So here is the source code for the client. This client first obtain the stub for the registry by invoking the static locate registry dot get registry method with the host name specified on the command line. If no host name is provided or if no host name is specified, the null is used as the host name, indicating that the local host address should be used. Next, the client invokes the remote method lookup on the registry stub to obtain the stub for the remote object from the server's registry. Finally, the client invokes say hello method on the remote object stub, which causes the following actions to happen. Client-side runtime opens a connection to the server using host and port information in the remote object stub, and then serialize the call data. Server-side runtime accept the incoming call dispatches the call to the remote object and serializes the result, the reply string, for example, saying hello world, to the client. And client side runtime receives, deserializes, and returns the result to the caller. As an exception example, we can consider remote exception. If remote communication with the registry failed, if exception is a server exception containing an access exception, then the registry denies the caller access to perform this operation. This method, this exception can be occurred, for example, lookup string method in interface registry. As an example, too, we can consider this java.rmi property, java.rmi.server.codebase. This property specifies the locations from which classes that are published by this VM, for example, stub classes, custom classes that implement the declared return type of a remote method call, or interfaces used by a proxy or stub class may be downloaded. The value of this property is a string in URL format, or a space separated list of URLs that will be the codebase annotation for all classes loaded from the class path of and subsequently marshaled by this VM. Note, this property must be set correctly in order to dynamically download classes and interfaces using Java remote method invocation, Java RMI. If this property is not set correctly, you will like to encounter exceptions when attempting to run your server or client. As an example 3, we can consider this. This is starting the client in Microsoft Windows. In this particular example, once the registry and the specific engine for this program are running, you can start the client specifying the following. The location where the client serves its classes here for by using the java.rmi.server.codebase property. The java.security.policy property, which is used to specify the security policy file that contains the permissions you intend to grant to various pieces of code. And as command line arguments, the hostname of the server, so that the client knows where to locate the remote object, and the number of the host name so that the client knows where to locate the remote object, uh, and the number of decimal places in this particular example to calculate value of 5 in this particular example specifically. Note that the class path is set on the command line so that the interpreter can find the client classes and the jar file containing the interfaces. Also note that the value of java.rmi.server.codebase property, which specifies a directory hierarchy, ends with a trailing slash. Now we are considering the remote interface in client interface. In RMI, a remote interface is an interface that declares a set of methods that may be invoked from a remote Java virtual machine. Interface remote. The remote interface serves to identify interfaces whose methods may be invoked from a non-local virtual machine. Any object that is a remote object must directly or indirectly implement this interface. Only those methods specified in a remote interface, an interface that extend java.rmi.remote, are available remotely. This is in the package java.rmi, which is in the module java.rmi. Now we are considering exception example remote exception. The remote exception class remote exception. A remote exception is the common superclass for a number of communication related exceptions that may occur during the execution of a remote method call. Each method of a remote interface, an interface that extend java.rmi.remote, must list remote exception in its throws clause. This is in the package java.rmi, which is in the module java.rmi. Now we are considering the naming class. Class naming. The naming class provides method for storing and method obtaining references to remote objects in a remote object registry. Each method of the naming class takes as one of its argument a name that is a java.lang.string in a URL format without scheme component of the form //host :port /name, where the host is the host remote or local where the registry is located. Port is the port number on which the registry accepts calls, and where the name is a simple string and uninterpreted by the registry. Both host and the port are optional. If the host is omitted, the host default to the local host. If the port is omitted, then the port default to the 199, the well-known port that RMI registry uses. Now we are considering Java RMI implementation logging. The property name sun.rmi.client.log calls, the logo name sun.rmi.client.call. Information logged here, client-side remote calls and exceptions. Now we are focusing on server program. A typical server program creates some remote objects, make references to these objects accessible, and wait for clients to invoke methods on these objects. Here this diagram is with about downloading Java RMI stubs with related to dynamic code downloading using Java RMI using the java.rmi.server.codebase property. Using Java RMI, applications can create remote objects that can accept method calls from clients in other VMs. In order for a client to call methods on a remote object, a client must have a way to communicate with the remote object. Rather than having to program the client to speak the remote object's protocol, Java RMI uses special classes called stubs that can be downloaded to the client that are used to communicate with to make method calls on the remote object. The java.rmi.server codebase property value represent one or more URL locations from which these stubs and any classes needed by the stubs can be downloaded. Like applets, the classes needed to execute remote method calls can be downloaded from file :////URLs, but like applets, a file :////URL generally requires that the client and the server reside on the same physical host, unless the file system referred to by the URL is made available using some other protocol such as NFS. Generally, the classes needed to execute remote method calls should be made accessible from a network resource such as an HTTP or FTP server. Here is step 1. The remote object's code base is specified by the remote object server by setting java.rmi.server.codebase property. The Java RMI server registers the remote object bound to a name with the RMI registry. The codebase set on the server VM is annotated to the remote object reference in the Java RMI registry. Number 2, step 2, the Java RMI client requests a reference to a named remote object. The reference, the remote object stub instance, is what the client will use to make remote method calls to the remote object. Step 3, the Java RMI registry returns a reference, a stub instance to the requested class. If the class definition for the stub instance can be found locally in the client's class path, which is always searched before the code base, the client will load the class locally. However, if the definition for the stub is not found in the client's class path, the client will attempt to retrieve the class definition from the remote code base object. Step 4, the client requests the class definition from the code base. The code base the client uses is the URL that was annotated to the stub instance when the stub class was loaded by the registry. Back in step 1, the annotated stub for the exported object was then registered with the RMI registry bound to a name. Step 5, the class definition for the stub and any other classes that it needs is downloaded to the client. Note, step 4 and 5 are the same steps that the registry took to load the remote object class when the remote object was bound to a class name in registered with the Java RMI registry. When the registry attempted to load the remote object stub class, if it requested the class definition from the code base associated with the remote object. Step 6, now the client has all the information that it needs to invoke remote methods on the remote object. The stub instance acts as a proxy to the remote object that exists on the server. So unlike applet, which uses code base to execute in its local VM, the Java RMI client uses the remote object's code base to execute code in another potentially remote VM, as shown here. So here, server that exported the remote object, and here the java.rmi.server.codebase equal URL here, and server registers a remote object bound to a name from server that exported the remote objects to RMI registry. And then in step 2, this is RMI client, and RMI client makes a naming lookup call to RMI registry. Then RMI registry returns an instance of the remote object stub to RMI client. Then RMI client requests the stub class from the code base. This is the URL location in my host. Then HTTP server returns the remote object stub class to client, and finally the RMI client makes a remote method call to remote object instance here. As an example, we can consider these code segments to implement the server. A remote object is an instance of a class that implement remote interface Remote interface extend the interface java.rmi.remote and declares a set of remote methods. Each remote method must declare java.rmi.remote exception or a superclass of remote exception in its throws clause, in addition to any application specific exceptions. Here is a interface definition for a remote interface. As an example, it declares one method which returns a string to the caller. Remote method invocation can fail in many additional ways compared to local method invocation, such as network related communication problems and server problems, and remote methods will report such failures by throwing a java.rmi.remote exception. A server class here in this context is the class which has the main method that creates an instance of the remote object implementation, exports the remote object, and then bind that object bind that instance to a name in a Java RMI registry. This the class that contains main method could be implementation class itself or another class entirely. In this example here, the main method for the server is defined in the server class, which also implements the remote interface hello. The server's main method does the following: create and export a remote object and register the remote object with a RMI registry. Implementation of class server implements the remote interface hello, providing an implementation for the remote method say hello. The method say hello does not need to declare that it throws any exception because the method implementation itself does not throw remote exception, nor does it throw any other checked exceptions. Note, a class can define methods not specified in the remote interface but those methods can only be invoked within the virtual machine running the service and cannot be invoked remotely. Now we are considering create and export a remote object. The main method in the server needs to create the remote object that provides the service. Additionally, the remote object must be exported to the Java RMI runtime so that it may receive incoming remote calls. This can be done as follows here. The static method unicast remote object dot export object exports the supplied remote object to receive incoming remote method invocation on an anonymous TCP port and returns the stub for the remote object to pass to clients. As a result of the export object call, the runtime may begin to listen on the new server socket or may use the shared server socket to accept incoming remote calls for the remote object. The return stub implements the same set of remote interfaces as the remote objects class and contains hostname and port over which the remote object can be contacted. Note, as of J2SC 5.0 release, stub classes for the remote objects no longer needed to be pre-generated using the RMIC stub compiler unless the remote object need to support clients running in pre 5.0 VMs. If your application needs to support such clients, you will need to generate stub classes for the remote objects used in the application and deploy those stub classes for clients to download. Now we are focusing on register the remote object with Java RMI registry. For a caller, client, peer or applet to be able to invoke a method on a remote object, the caller must first obtain the stub for the remote object. For bootstrapping, Java RMI provides a registry API for applications to bind a name to a remote object stub for clients to look up the remote objects by name in order to obtain their stubs. The RMI registry is a simplified name service that allows clients to get a stub to a remote object. In general, a registry is used, if at all, only to locate the first remote object a client needs to use. Then typically the first object would be in turn provide application specific support for finding other objects. For example, the reference can be obtained as a parameter to or return a value from another remote object's call. Once a remote object is registered on a server, callers can look up the object by name, obtain a remote object reference, and then invoke remote methods on the object. In this code here in the server, obtain the stub for the registry on the local host and default registry port, and then uses the registry stub to bind the name hello to the remote object's stub in the registry. The static method local registry dot get registry that takes no arguments returns a stub that implements the remote interface java.rmi.registry and sends the invocation to the registry on server's local host on the default registry port of 1099. The bind method is then invoked on the registry stub in order to bind the remote object stub name hello in the registry. Note the call to locate registry get registry simply returns an appropriate stub for the registry. The call does not check to see if a registry is actually running. If no registry is running on the TCP port 1099 of the local host, when the bind method is called, bind method is invoked, the server will fail with remote exception. Here the method getRegistry returns a reference to the remote object registry for the local host on the default registry port 1099. And here the interface remote. The remote interface serves to identify interfaces whose methods may be invoked from a non-local virtual machine. Any object that is a remote object must directly or indirectly implement this interface. Only those methods specified the remote interface an interface that extends the java.rmi. Remote are available remotely. Interface remote. The remote interface serves to identify interfaces whose methods may be invoked in non-local virtual machine. Any object that is a remote object must directly or indirectly implement this interface. Only those methods specified in the remote interface, an interface that extend java.rmi.remote are available remotely. As an example 2, we can consider this property java.rmi.server.hostname property. The value of this property represent the hostname string that should be associated with remote stubs for locally created remote objects. In order to allow clients to invoke methods on the remote object, the default value of this property is the IP address of the local host in dotted quad format. As example 3, we can consider this one starting the server in Microsoft Windows, and before starting the You need to start the RMI registry. RMI registry is a simple server-side bootstrap naming facility that enables remote clients to obtain a reference to an initial remote object. It can be started with the RMI registry command. Before you execute RMI registry, you must make sure that the shell or window in which you run the RMI registry either has no class path environment variable set or has a class path environment variable that does not include the path to any classes that you want to download it to clients in your remote objects. To start the registry on the server, execute RMI registry command. This command produces no output and is typically run in the background. For example, this is for the Windows. Use Java W if start is not available. Once the registry is started, you can start the server. You need to make sure that both this Java file and the remote object implementation classes are in your class path. When you start, you have to specify the java.rmi.server.codebase property where the server's classes are network accessible. In this example, the server-side classes to be made available for downloading are here, and which are available in the compute.jar file in the public _html and / classes directory of user and here. So the service started. So we started on the host my computer. The same host on which the registry was started. This property, the java.rmi.server.codebase property, specify the location, a codebase URL from which the definition for the classes originating from this server can be downloaded. If the codebase specify a directory hierarchy as opposed to a jar file, you must include the trailing slash at the end of the codebase URL. The java.rmi.server.hostname property specify the hostname or address to put in the stubs for remote objects exported in this Java virtual machine. This value is the hostname or address used by the client when they attempt to communicate remote method invocations. By default, RMI implementation uses the server's IP address as indicated by the java.net.inetaddress.getLocationHost API. However, sometimes this address is not appropriate for all clients and a fully qualified hostname would be more effective. To ensure RMI uses the hostname or IP address for server that is routable from all potential client set the java.rmi.server.hostname property. The java.security.policy property is used to specify the policy file that contains the permissions you intended to grant. Now we are considering package java.rmi.server. Provide classes and interfaces for supporting the server side of RMI. One group of classes are used by the static stubs and skeletons. Another group of classes implements RMI transport protocol. Deprecated skeletons and static stubs. Skeletons and statistically generated stubs are deprecated. This provides the APIs in this package that require the use of skeletons or static stubs and the runtime support for them. Support for skeletons and static stubs may be removed in future release of the platform. Skeletons are unnecessary as server-side method dispatching is handled directly by the RMI runtime. Statistically generated stubs are necessary as stubs are generated dynamically using proxy object. See unicast remote object for information about dynamic stub generation. Now this package is in the module java.rmi. Now we are considering the remote server class. This is in the package java.rmi.server, which is in the module java.rmi. The class remote server. The remote server class is the common superclass to server implementations and provides the framework to support a wide range of remote reference semantics. Specifically, the functions needed to create and export remote objects, that is, to make them remotely available, are provided abstractly by remote server and concretely by its subclasses. Now we are considering the RMI Security Manager class. The class RMI Security Manager. The RMI Security Manager implements a policy identical to the policy implemented by Security Manager. RMI application should use the Security Manager class or another appropriate Security Manager implementation instead of this class. RMI's class loader will download the classes from remote locations only if a Security Manager has been set. This is deprecated for removal. This API element is subject to removal in future version. This class is only useful in conjunction with the Security Manager, which is deprecated and subject to removal in future release. Consequently, this class is also deprecated and subject to removal. This is no replacement for Security Manager or this class. This is in the package java.rmi and which is in the module java.rmi. Now we are considering Java RMI class loader class. RMI class loader. RMI class loader comprises statics method to support dynamic class loading with RMI. Included are methods for loading classes from the network locations, one or more URLs, and obtaining the location from which the existing class should be loaded by remote parties. These methods are used by the RMI runtime when marshalling and unmarshalling classes contained in the arguments and return values to remote method calls, and they also may be invoked directly by application in order to mimic RMI's dynamic class loading behavior. This is in the package java.rmi.server and which is in the module java.rmi. Now we are considering the loader handler interface. Interface loader handler, deprecated and no replacement. Loader handler is an interface used internally by the RMI runtime in previous implementation versions. It should never be accessed by application code. This is in the package java.rmi.server and which is in the module java.rmi. Now we are considering RMI socket factory class in in RMI socket factories. Note that the class below uses socket and server socket from java.net package. RMI socket factory, class RMI socket factory. An RMI socket factory instance is used by the RMI runtime in order to obtain the client and server sockets for RMI calls. An application may use set socket factory method to request that RMI runtime use its socket factory instance instead of default implementation. This is in the package java.rmi.server, which is in the module java.rmi. Here the java.rmi.server RMI socket factory abstract class provide an interface for specifying how the transport should obtain sockets. Note that the class below uses socket and server socket from the .NET package. Static method set socket factory is used to set the socket factory from which RMI obtains sockets. The application may invoke this method with its own RMI socket factory instance only once. The application defined implementation of RMI socket factories could, for example, do primarily filtering on the requested connection and throw exceptions, or return its own extension of java.net.socket or java.net.server socket classes, such as ones that provide a secure communication channel. Note that the RMI socket factory may only be set if the current security manager allows setting socket factories. If setting socket factory is disallowed, the security exception will be thrown. The static method get socket factory returns the socket factory used by RMI. The method returns null if the socket factory is not set. The transport layer invokes create socket and create server socket methods on the RMI socket factory returned by the get socket factory method when the transport needs to create sockets. For example, RMI socket factory dot get socket factory method dot create socket factory my host my port. The method create socket should create a client socket connected to the specific host and port. The method create server socket should create a server socket on the specified port. The default transports implementation of RMI socket factory provides provides for transparent RMI through firewalls using HTTP as follows. The create socket, the factory automatically attempts to HTTP connections to hosts that cannot be connected with direct socket. On create server socket, the factory returns a server socket that automatically detects if the newly accepted connection is an HTTP post request, so that it returns the socket that will transparently export only by the only by the body of the requested transport and format its output as HTTP response. The method set failure handler sets the failure handler to be called by the RMI runtime if the creation of a server socket fails. The failure handler returns the boolean to indicate if retry should occur. The default failure handler returns false, meaning that by default recreation of sockets is not attempted by the runtime. The method get failure handler returns the current handler for the socket socket creation failure or null if the failure handler is not set. Um, you you can use RMI socket factory class to create a server socket that bound to a specific address, restricting the origin of requests. For example, the following code implements a socket factory that binds the server socket to IP4 loopback address, IP version 4 loopback address. This restricts RMI to processing requests only from localhost. Set the RMI set the java.rmi.server.hostname system property to 127.0.0.1 to ensure that generated stubs connect to the right network interface. Just call the default client socket factory. Now we are considering the RMI failure handler interface. The java.rmi.server.RMI failure handler interface provides a method for specifying how the RMI runtime should respond when the server socket creates fails except during object export. The interface RMI failure handler. An RMI failure handler can be registered via the RMI socket factory.set failure handler call. The failure method of the handler is invoked when the RMI runtime is unable to create the server socket to listen to incoming calls. The failure method returns the boolean indicating whether the runtime should attempt to recreate the server socket. This is in the package java.rmi.server and which is in the module java.rmi. The java.rmi.server.rmi failure handler interface provides a method for specifying how the RMI runtime should respond when the server socket creation fails except during the object export. The failure method is invoked with the exception that prevented the RMI runtime from creating java.net server socket. The method returns true if the runtime should attempt to retry and false otherwise. Before this method can be invoked, a failure handler needs to be registered via the socket factory.set handler call. If the failure handler is not set, the RMI runtime attempts to recreate the server socket after waiting for a long period of time. Note that the RMI failure handler is not called when server socket creation fails upon initial export of the object. The RMI failure handler will be called when there is an attempt to create server socket after a failed accept on server socket. Now we are considering the logstream class logstream, deprecated, no replacement. Logstream provides a mechanism for logging errors that are of possible interest to those monitoring system. This is in the package java.rmi.server, which is in the module java.rmi. Here we are considering the stub and skeleton compiler. For example, the running RMIC on class file name hello impl as shown here. In Windows RMIC, the Java RMI compiler, the RMIC compiler generates stub and skeleton class files, JRMP protocol, and stub and TIE class files, IIOP protocol for remote objects. These class files are generated from compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements the interface Java .rmi.remote. The class names in the RMIC command must be of classes that have been compiled successfully with the Java C command and must be fully package qualified. For example, running RMIC on the class file name hello impl as shown here. In Unix RMIC, the deprecation not support for static generation of Java remote method protocol JRMP stubs and skeleton have been deprecated. Once recommends that you use the dynamically generated JRMP stubs instead, eliminating the need to use this tool for JRMP based applications. The RMIC compiler generates stubs and skeleton classes for using files using the Java remote method protocol JRMP and stub and tie class files IIOP protocol for remote objects. These class files are generated from compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements the remote interface java.rmi.remote. The class names in the RMIC command must be for classes that were compiled successfully in the Java C command and must be fully qualified. Must be fully package qualified. For example, running the RMIC command on the class file name hello impl as shown here creates the hello impl underscore stub.class file in the hello subdirectory named for the classes package. Now we are considering properties that are useful to set on virtual machines VMs that export remote objects in java.rmi properties. The java.rmi.server.codebase property. This property specifies the location from which classes that are published by this VM, for example, stub classes, custom classes that implement the declared return type of a remote method call or interfaces used by a proxy or stub class may be downloaded. The value of this property is a string in URL format or a space generated list of URLs that will be a code base annotation for all classes loaded from the class path of and subsequently marshaled by this VM. Note this property must be set correctly in order to dynamically download classes and interfaces using Java remote method invocation, Java RMI. If this property is not set correctly, you will likely encounter exceptions when attempting to run your server or client. For more information on this property, see dynamic code downloading using Java RMI in the documentation using the java.rmi.server.codebase property. Now we are considering properties that are useful to set on VMs that make remote method calls. Java.rmi.server.codebase. This property specifies the location from which the classes that are published by this VM, for example, custom classes that implements the interface that is the declared parameter of a remote method call may be downloaded. The value of this property is a space separated list of URLs that will be the code base annotation for all classes loaded from the class path of and subsequently marshaled by this VM. Note the classes that exist in both server code base and the client class path will be loaded from the client's class path rather than from the server's code base as intended. Now we are considering properties that can be set on our RMID in Java in sun.rmi properties. sun.rmi.server.activation.debug exec. If this value is true, the activation system will print out debugging information to the command line that is used for spawning activation groups. By default, the value is false, so debugging information is not printed. Now we are considering properties that are useful to set on VMs that export remote objects. Java.rmi.server.exception trace. This property controls the output of a server-side stack traces from exception and errors that are thrown by dispatched incoming remote calls. If this value is true, the exception stack traces will be printed. By default false. exception and error stack traces are not printed. Now we are considering Java RMI implementation logging. System property name java.rmi.server.localls. The logger name sun.rmi.server.call. Information logged, server-side remote calls and exceptions. As an exception example, we can consider server exception. A server exception is thrown as a result of a remote method invocation when remote exception is thrown while processing the invocation on the server, either while unmarshalling the argument or executing remote method itself. A server exception instance contains the original remote exceptions that occurred as its cause. The class server exception is in package java.rmi. As an error example, we can consider server error. The class server error. A server error is thrown as a result of a remote method invocation when an error is thrown while processing the invocation on the server, either while unmarshalling the argument, executing the remote method itself, or marshalling the return value. A server error instance contains the original error that occur as its cause. This class server error is in package java.rmi. Now we are focusing on stubs and skeletons. A stub for a remote object acts as a client's local representative or proxy for a remote object. The caller invokes a method on the local stub which is responsible for carrying out the method call on the remote object. In RMI, the stub for a remote object implements the same set of remote interfaces that a remote object implements. Here you can see RMI stub passing mechanisms. We have already seen that RMI client can obtain a stub to a RMI server via registry. But consider the fact that the stub is already but consider the fact that the stub is really just an object that is instantiated on the same machine as RMI server. That the registry serializes and send to the RMI client. Note, technically the registry does not have to be co-located on the same machine as RMI server object. Therefore, the stub may initially get serialized and sent to the registry machine before client requests it. And stubs can be passed in two other ways. Stub passed as an input parameter to another stubs method, and stub is stub returned by another stub method. So this has several implications, RMI stub can serve as factories for more stubs by returning stubs. Not all stubs need to be bound in the registry to be used, and some parts of the system may not need to bind a stub into registry at all. They send their stubs to other parts of the system via input parameter of methods of their stubs. At least one stub somewhere needs to be bound in the registry. That's the stub that starts everything else. A number of stubs bound in a registry should be kept to an absolute minimum, that is only one. More than one RMI client may use the same stub. Technically, different copies of the same stub from the RMI server machine. Stubs can be replicated by passing them around the network, creating multiple RMI clients all connected to the same RMI server. But we can see from these conclusions that if we bind a very few factory objects as stubs into the registry, that is only one from these factories, we can dynamically bind our networked system. But there's a drawback. Each stub consumes system resources in the form of allocated ports. Once a stub is tied to a port, the ability of other entities use that port is severely limited, if not completely excluded. This can severely impact the system and cause other headaches, such as having to reduce the system safely by opening more ports through the firewall. Here you can see RMI client machine, registry server, RMI server machine. Here you can see RMI stub is bind to the registry, and RMI stub lookup from registry from this RMI stub to the RMI client machine. And here you can see RMI server objects is here. RMI stub passed as input parameter to stub method. RMI stub here, and here you can see RMI server object here. RMI stub return from stub method here. Here you can see a proxy pattern. The stub and skeleton layer of RMI lie just beneath the view of the Java developer. In this layer, RMI uses the proxy design pattern as described in the book Design Patterns by Gamma, Helm, Johnson and Lizards. In the proxy pattern, an object in one context is represented by another proxy in a separate context. The proxy knows how to forward method calls between the participating objects. This diagram illustrates the proxy pattern. The RMI of the proxy pattern, the stub class plays the role of the proxy, and the remote service implementation class plays the role of real subject. And a skeleton is a helper class that is generated from RMI to use. Skeleton understand how to communicate with stub across the RMI link, and skeleton carries a conversation with the stub. It reads parameters for the method call from the link, makes a call to the remote service implementation object, accept and return value, and then writes the return value back to the stub. In the Java 2 SDK implementation of RMI, the new wire protocol has made skeleton classes obsolete. RMI uses reflection to make connection to the remote service object. You only have to worry about skeleton classes and objects in JDK 1.1 and JDK 1.1 compatible system implementation. In this diagram, we are considering about the proxy pattern with related to stubs. Here you can see the subject interface and the request method, and in proxy is connected to real subject, and real subject is passed from proxy to real subject. Here you can see some stubs and skeletons. Remote clients communicate with server object via stubs and skeletons. These stubs and skeletons are automatically produced by the Java compiler on class files that extend unicast remote object and have an interface that extend remote. These stubs and skeletons are implementation of proxy design pattern, which is related to decorator design pattern. Stubs and skeletons are adapters that first adapt the client to the internet, and then the internet to the server object. Any serializable object that is implement serializable can be transmitted to the server by use of an input parameter if a method of the iRemote object interface. Any serializable object can be sent to the client by use of a return value of a method of iRemote interface. Any method of a serializable non-unicast remote object set to the client run on the client. A class server must be running in order for the RMI registry to initially load the stubs in preparation for transmitting them to clients. Here you can see a client with the iRemote object. The remote object appears local to the client here, and here you can see iRemote object. The client deals with an interface, not the remote object directly. Here you can see remote indicates that the object is remote. And here you can see remote object stub, remote object skeleton. On the client side, the stub is transmitted to the client when the client asks the server's RMI registry for the client for the object bound to a specific name. And here you can see remote object skeleton, object, remote object. On the server side, the stub communicate with the skeleton, not with the remote object directly. You can see the remote object here, the object that the server wishes to remote clients to use. And here you can see unicast remote object contains the code necessary to create stubs and skeletons. Now we are considering how code base is used in Java RMI. Here you can see downloading Java RMI stubs. Using Java RMI, applications can create remote objects that accept method calls from clients in other VMs. In order for a client to call methods on a remote object, the client must have a way to communicate with the remote object. Rather than having to program the client to speak the remote object's protocol, Java RMI uses special classes called stubs that can be downloaded to the client. That are used to communicate with make method calls on the remote object. The java.rmi.server.codebase property value represent one or more URL locations from which these stubs and any classes needed by stubs can be downloaded. Like applets, the classes needed to execute remote method calls can be downloaded from file :////URLs, but like applets, a file : URL generally requires the client and servers reside on the same physical host unless the file system referred to by the URLs made available using some other protocol such as NFS. Generally, the classes needed to execute remote method calls should be made accessible from a network resource such as HTTP or FTP server. Remote objects code base is specified by the remote object server by setting the java.rmi.server.codebase property. The Java RMI server registers a remote object bound to the name, and with the Java RMI registry, codebase set on the server VM is annotated to the remote object reference in the Java RMI registry. Java RMI client requests a reference to a named remote object. The remote object stub instance is what the client will use to make remote methods calls to the remote object. 3. The Java RMI registry returns a reference, the stub instance, to the requested class. If the class definition for the stub instance can be found locally in the client's class path, which is always searched before the code base, the client will load the class locally. However, if the definition for the stub is not found in the client's class path, the client will attempt to retrieve the class definition from the remote object's code base. 4. The client requests the class definition from the code base. The code base client uses is the URL that was annotated to the stub instance when the stub class was loaded by the registry. Back in step 1, the annotated stub for the exported object was then registered with the Java RMI registry bound to the name. 5. The class definition for the stub or any other classes that needs is downloaded to the client. Note step 5, 4 and 5 are the same steps that the registry took to load the remote object class uh, when the remote object was bound to a name in registered the Java RMI registry, when the registry attempted to load the remote object stub class, it requested the class definition from the code base associated with that remote object. 6 Now the client has all the information that it needs to invoke the remote method on the remote object. The stub instance acts as a proxy to the remote object that exists on the server. So unlike the applets which uses the code base to execute the code in its local VM, the remote RMI client uses the remote object's code base to execute code in another potentially remote VM, as illustrated in this figure. Using code base in Java RMI for more than just stub downloading here. In addition to downloading stub and associated classes to client, the java.rmi.server.codebase property can be used to specify location in which any class, not only the stubs, can be downloaded. When the client makes method call to a remote object, the method that it calls could be written to accept no arguments or a number of arguments. There are 3 distinct classes that may occur based on the Java data types of the method arguments. The first case, all of the method parameters and return values are primitive data types, so the remote object knows how to interpret them as method parameters, and there is no need to check class path or any code base. The second case is that the remote method parameter or return value is an object for which the remote object can find the class definition locally, its class path. In the third case, shown in step 6, in this figure, the remote method receives an object instance for which the remote object cannot find the class definition locally in its class path. This type of remote method call is illustrated in figure 4 here, this figure. The class of the object sent by the client will be a subtype of declared parameter type. The subtype is either an implementation of the interface that is declared as the method parameter or return type, a class of the class that is declared as the method parameter or return type. You can see here Java RMI client making a remote method call passing an unknown subtype as the method parameter. And here is step 7, like the applet code base, the client specified code base is used to download remote classes, non-remote classes and interfaces to other VMs. If the code base property is set on the client's application, then the code base is annotated to the subtype instance when the subtype class is loaded by the client. If the code base is not set on the client, the remote object will mistakenly use its code base. Here you can see a server that exported a remote object here. Server registers a remote object bound to a name. Here step 1 is connecting a server that exported remote object, and here the java.rmi.server.codebase equal this address, and it's connected to server that registers a remote object bound to a name. And here step 2, RMI client is connected to RMI registry via client makes a naming.lookup call. Here step 3, RMI registry is connected to RMI client via the registry returns an instance of the remote object stub. Here RMI client is connected to URL location and my host here via client requests the stub class from the code base. Here my host or URL location here is connected to RMI client via HTTP server returns remote objects stub class. Here my host here URL location interacts with RMI registry. Here here step 6, RMI client is connected to remote object instance makes a remote method call. Here you can see RMI registry, and here server that exported the remote object. Here is step 6. Here RMI client is connected to remote object instance. Clients make a remote method call passing a subtype unknown to the remote object as a remote method parameter. And here RMI client interacts with URL location. Here you can see the code base, and via code base property. Here remote object instance interacts with URL location via remote object downloads the subtypes class definition from the client specified code base. And consider this code segment. This stub object automatically created from this remote objects class file. This RMI stub object is instantiated by the same application that holds the RMI server object. The RMI stub object is transmitted to the client whenever a reference to the remotely accessible object RMI server object is established. This is actually this is the actual object that the client interacts with. The stub object simply delegates all methods across the network to its corresponding skeleton objects on the server. Here you can see the stub method is called. When a stub method is invoked, it does the following: initiate the connection with the remote JVM containing the remote object, marshals, writes and transmit the parameters to the remote JVM, wait for the result of the method invocation, unmarshals, read the return value or exception return, and returns the value to the caller. Stub hides the serialization of parameters and network level communication in order to present the simple invocation mechanism to the caller. For the here you can see register the remote object with Java RMI registry. A caller, client, peer or applet to be able to invoke a method on the remote object, the caller must first obtain a stub for the remote object. For bootstrapping, Java RMI provide a registry API API for applications to bind a name to a remote object stub, and for clients to look up the remote objects by name in order to obtain their stubs. In Java RMI registry, a Java RMI registry is a simplified name service that allows clients to get a reference to a stub to a remote object. In general, a registry is used, if at all, only to locate the first remote object a client needs to use. Then typically the first object would in turn provide application specific support for by finding other objects. For example, the reference can be obtained as a parameter or parameter 2 or a return value from another remote method call. Once a remote object is registered on the server, caller can look up the object by name, obtain the remote object reference, and then invoke the remote methods on the objects. In this code, the server obtains a stub for a registry on the local host and default registry port, and then uses registry stub to bind the name hello to the remote object stub in the registry. The static method local registry.get registry that takes no arguments and returns a stub that implements the remote interface java.rmi.registry.registry and send invocations to the registry on the server's local host on default registry port of 1099. The bind methods is then invoked on the registry stub in order to bind the remote object stub to the name hello in the registry. Note, the call to locate registry.get registry simply returns an appropriate stub for a registry. The call does not check to see if a registry is actually running. If no registry is running on TCP port 1099 of the local host when the bind method is invoked, the server will fail with the remote exception. As an example, we can consider this java.rmi property, java.rmi server.codebase. This property specifies the locations from which classes that are published by this VM. For example, stub classes, custom classes that implement the declared return type of a remote method call, or interfaces used by a proxy or stub class may be downloaded. The value of this property is a string in URL format or a space separated list of URLs that will be the code base annotation for all classes loaded from the class path of and subsequently marshaled by this VM. Note, this property must be set correctly in order to dynamically download classes and interfaces using Java remote method invocation, Java RMI. If this property is not set correctly, you will likely encounter exceptions when attempting to run your server or client. As an exception example, we can consider this one: stub not found exception. Class stub not found exception. A stub not found exception is thrown if a valid stub class could not be found for a remote object when it is exported. A stub not found exception may also be thrown when an activatable object is registered via the java.rmi.activation.activatable.register method. This exception is in package java.rmi. As an error example, we can consider this error. It is occurred when creating. It was occurring when creating EDQ data server in DIPCC Governance Edition ODI Studio client. Failed to retrieve RMI server stub. javax.naming.service unavailable exception root exception is java.rmi.connection exception, connection refused to host, localhost. Nested exception is java.net.connection exception, connection timeout at javax.management.remote.rmi.rmiconnector.connect, rmiconnector.java, etc. Now we are considering stubs and skeleton related to client program. A skeleton for a remote object is a JRMP protocol server-side entity that has a method that dispatches calls to the actual remote object implementation. Here you can see how RMI architecture compares to the open system integration OSI architecture. The RMI application layer like OSI application layer contains the application programs. The stub and skeleton layer is similar to the OSI presentation layer in that it manages the remote object interface between client and server. The skeleton communicates with the stub except in Java 2.0 or higher, which has no skeleton. Once it obtain a reference to the remote object, the client can invoke it and receive the arguments of the operations allowed. The stub marshals and unmarshals the argument sent over the connection. OSI session layer is similar to the RMI layer that obtains a reference to the remote object from the naming registry service module. Finally, TCP, the TCP/IP network protocol packets encapsulates the transport layer. Transport layer contains Java remote method protocol JRMP, also called the wire protocol. This shows RMI's architecture maps easily to the layers of more common open system integration OSI model. RMI architecture is highly suited for application servers that accepts code, data, and method calls from clients on fly. Persistent references let RMI control the number of active objects. The server can deactivate some objects so that the other objects can do their work. A client could reactivate the object on demand. Applications with many servers resulting many object references would benefit from RMI. Examples include airline reservation systems and enterprise-wide document archiving systems. Here you can see client application interact with the stub, and stub interact with remote reference layer. Remote reference layer interact with Java remote method protocol. Java remote method protocol interacts with remote reference layer and remote reference layer is there, and JDK versions prior to 2.1 used a skeleton stub at this point, and skeleton stub is connected to applications, server application and remote reference layer. Here you can see with OS layers. In application layer you can see a client application and server application. In presentation layer you can see stub and skeleton. In session layer you can see a remote reference layer. Transport network layer you can see Java remote method protocol. Here you can see another diagram of RMI architecture. RMI gives a way for Java program on one machine to interact with object residing on different JVMs. The important blocks of RMI architecture are stub classes, skeleton classes, and object serialization. RMI needs a layered architecture where each of the layers may be enhanced without affecting other layers. Layers may be defined as this: application layer, a server, and the client program. Skeleton and stub layer, intercept method invokes made by the client and redirect these calls to remote RMI service. Remote reference layer, setups connection to remote address spaces, understand and manages connection, how to manage, interpret references given from clients to the remote service objects. Transport layer, based on the TCP/IP connections between operating system in the network, it gives a basic connectivity as well as some firewall penetration goals. RMI stub classes give a reference to a skeleton object located in a different address space on the different or same machine. This is typical example of proxy design pattern, which builds an object executing another JVM seems like a local object. In JDK 5.0 and later, RMI facility access dynamic proxy instead of generated stubs, which build RMI easier to use. Here you can see client object looks up the stub in RMI registry and OGNID server, and RMI registry returns a stub to client object. Then stub method call on remote server objects to on skeleton, and skeleton send result and exception to stub. And here you can see the client and server is connected through cloud or network. Client is connected to the client process. Inside the client process you can see a client object, stub, and remote reference manager. Client object is connected, interact with stub. Stub interact with remote reference manager. And here you can see the server process. It has RMI registry, remote object, skeleton, and remote reference manager. Remote reference manager in client process is connected through RMI transport layer to remote reference manager in server process. and remote iframe manager interacts with skeleton. Skeleton interacts with remote objects. And here you can see load stubs to RMI registry, and server is connected to server process. Here the note steps 4 and 5 are logical explanation only. Neither the stubs nor skeletons use sockets directly. The actual calls are made through the remote reference manager. Remote reference manager handles the actual details of communicating with remote process. This extra layer manages network communication and conserve scarce resources like sockets. Here you can see program 1 stub is connected to the skeleton, program 2 stub is connected to skeleton in program 1. We can consider this code segment as an example. The interface skeleton is deprecated, and the skeleton interface is used solely by the RMI implementation. Every version 1.1 and version 1.1 compatible skeletons generated in 1.2 using RMIC-V compact. Skeleton class generated by the RMIC stub compiler implements this interface. A skeleton for a remote object is a server-side entity that dispatches call to the actual remote object implementation. This interface is in java.rmi server. In the Java 2 SDK standard edition version 1.2, an additional stub protocol was introduced that eliminate the need for skeletons in Java 2 platform-only environments. Instead, generic code is used to carry out the duties performed by skeletons in Java 1.1. Stubs and skeletons are generated by RMIC compiler. As an example, we can consider exception. If a general exception occurs in method void dispatch remote call int long in skeleton in interface skeleton. As an exception example 2, we can consider skeleton not found exception. It's a deprecated one. A class skeleton not found exception. No replacement. Skeletons are no longer required for remote method calls in Java 2 platform version 1.2 or greater. This is in package java.rmi.server. As an example 2, we can consider this example with the RMIC. When this command completes, the stub and skeleton should be located in the directory with the rest of the .class files. RMIC, the RMIC compiler generates stub and skeleton class files, JRMP protocol, and stub and tie class files, IIOP protocol for remote objects. These classes files are generated from compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements interface java.rmi.remote. The class names in the RMIC command must be for the classes that have been compiled successfully with the javac command and must be fully package qualified. By default, RMIC generates stub classes that use the 1.2 JRMP stub protocol version only, as if the version 1.2 option had been specified. Note that the -v compact option was the default in releases prior to 5.0. Use the -IIOP option to generate stub and tie classes for the IIOP protocol. As an error example, we can consider this one. This error occurred while running this command RMIC my remote impl invalid URL string, invalid URL string remote hello at java.rmi.naming.past URL at java.rmi.naming.rebind at RMI service.myremote.implementation.main caused by java.net.uri syntax exception illegal character in path at index 6 remote hello, etc. As an example 3, we can consider this one. In the remote JVM, each remote object may have a corresponding skeleton. In Java 2 platform only environments, skeletons are not required. The skeleton is responsible for dispatching the call to the actual remote object implementation. When a skeleton is received, an incoming method invocation, it does the following: unmarshals read the parameters for the remote method, invokes the method on the actual remote object implementation, and marshals writes and transmit the result, return value or exception to the caller. In Java 2 SDK standard edition version 1.2, an additional stub protocol was introduced that eliminates the need for skeletons in Java 2 platform only environment. Instead, generic code is used to carry out the duties performed by skeletons in JDK 1.1. Stubs and skeletons are generated by RMIC compiler. Here you can see the stubs here with Java 2 SDK, the server side. Here you can see we can take this as example 4 compile source files, where dest_dir is the destination directory to put the class files. Note that if server needs to support client running on pre 5.0 VMs, then the stub class for the remote object implementation class needs to be pre-generated using the RMIC compiler, and that stub class need to be made available for clients to download. Now we are considering stubs and skeletons layer. The stubs skeleton layer is the interface between the application layer and the rest of the RMI system. This layer does not deal with specifies of any transport, but transmit data to the remote reference layer via the abstraction of Marshall streams. Marshall streams employ a mechanism called pickling, which enables Java objects to be transmitted between address spaces. Objects transmitted using the pickling system are passed by copy to the remote address space. Here you can see the relationship among remote object, stub, and skeleton classes. Defining remote RMI object involves specifying a remote interface for the object, but then providing class that implements this interface. The remote interface and the implementation class are then used by RMI to generate the client stub and server skeleton for your remote object. The communication between local objects and remote objects is handled using these client stubs and server skeletons. Relationship among stubs and skeleton and object that use them are shown in this figure. When a client gets a reference to a remote object, details on how this reference is obtained we discuss later, and then calls methods on this object reference. There needs to be a way for the method request to get transmitted back to the actual object on the remote server, and for the results of the method call to get transmitted back to the client. This is what the generated stub and skeleton classes are for. They act as a communication link between client and your exported remote object, making it seem to the client that object actually exists within Java. Within its Java VM. The RMI compiler, RMIC, automatically generates this stub and skeleton classes for you based on the remote interface and implementation class you provide. RMIC generates stub and skeleton classes that implements remote interface and act as go between the client application and the actual server object. The client stub class, the compiler generates an implementation of each remote method that simply packages up marshals the method arguments and transmit them to the server. For the server skeleton class, the RMI compiler generates another set of implementation of remote methods. Remote method call, unpackage them and make the corresponding method call on object implementation. Whenever the method call generates a return data or an exception, the results are packaged and transmitted back to the remote client. The client stub method, which is still executing at this point, unpackages the result and delivers them to the client as the result of its remote method call. So the first step of creating your remote object is define the remote interface for the types of objects you need to use in the distributed object context. This isn't much different from defining public interfaces in a non-distributed application, with the following exceptions. First point, every object you want to distribute using RMI has to directly or indirectly extend an interface that extend java.rmi.remote interface. Every method in the remote interface has to declare that it throws java.rmi.remote exception or one of the parent classes of remote exception. Note that prior to Java 1.2, the RMI specification required that every method on a remote interface had to throw remote exception specifically. In Java 1.2, this has been loosened to allow any superclass of remote exception. Reason for this change is to make it easier to define generic interfaces that support both local and remote objects. RMI imposes the first requirement to allow it to differentiate quickly between objects that are enabled for remote distribution and those that are not. As we have already seen, during a remote method invocation, the RMI runtime needs to be able to determine whether each argument to the remote method is a remote object or not. The remote interface, which is simply a tag interface that marks remote objects, make it easy to perform this check. The second requirement is needed to deal with errors that can happen during remote session. When a client makes a method call on a remote object, a number of errors can occur, preventing a remote method call from completing. These may include client-side errors. An argument can't be marshaled. Errors during the transport of data between client and server. For example, network connection is dropped. And errors on the server side, for example, method throws a local exception that needs to be sent back to the remote caller. The remote exception class is used by RMI as a base exception class for any different types of problems that might occur during remote method call. Any method you declare on a remote interface is assumed to be remotely callable, so every method has to declare that it might throw a remote exception or one of its parent interfaces. Here you can see this is step 1, define remote interfaces. Step 2, define server implementations. Step 3, generate stubs and skeleton using RMIC. Here you can see stub and skeleton are connected to remote interface, and here you can see the inheritance lines. Here implementation of remote interface is connected to remote interface. Here you can see the inheritance line, and here implementation of remote interface is connected to stub and skeleton class. Here you can see generated by RMC line arrow. Here implementation of remote interface is connected to remote object implementations. Here you can see instances arrow. Here stub class is connected to stub object, and you can see here instances arrow. Here skeleton class is connected to skeleton object. Here you can see instances arrow. And here client object is client object interacts with stub object. Here skeleton object interacts with remote object implementation. Here you can see communication arrows in both way. Here also. Here the remote interface and implementation of interface, implementation of remote interface interfaces or classes written by you. Here the stub class and skeleton class are interfaces or classes generated from RMIC. Here client objects and remote object implementations are objects created by you, and here stub object and skeleton objects are objects created by RMI. Now we are considering stubs. Here stubs and skeletons. RMI uses a standard mechanism employed in RPC systems for communicating with remote objects, stubs and skeletons. A stub for a remote object acts as a client local representative or proxy for the remote object. The caller invokes a method on the local stub which is responsible for carrying out the method call on the remote object. In RMI, a stub for a remote object implements the same set of remote interfaces that the remote object implements. When a stub method is invoked, it does the following: initiate a connection with the remote JVM containing the remote object, marshals write transmits the parameters to the remote JVM, wait for the result of the method invocation, marshals reads the return value, unmarshals reads the return value or exception returns and returns the value to the caller. The stub hides in the serialization of the parameters and the network level communication in order to present the simple invocation mechanism for the caller. In the remote JVM, each remote object may have a corresponding skeleton. In Java 2 platform, only environment skeletons are not required. The skeleton is responsible for dispatching the call to the actual remote object implementation. When a skeleton receives an incoming method invocation, it does the following: unmarshals read the parameters for remote method, invokes the method on the actual remote object implementation, and marshals writes and transmits the result return value or exception to the caller. In Java 2 SDK, Standard Edition version 1.2, an additional stub protocol was introduced that eliminates the need for skeleton in Java 2 platform only environment. Instead, generic code is used to carry out the duties performed by skeletons in JDK 1.1. Stubs and skeletons are generated by RMIC compiler. Now we are considering stub and skeleton compiler. The RMIC stub and skeleton compiler is used to compile the appropriate stubs and skeletons for specific remote object implementation. For the Windows RMIC here, the Java RMIC compiler, the RMIC compiler generates stubs and skeleton class files, JRMP protocol, and stub and tie class files, IIOP protocol for remote object. These classes files are generated from compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements the interface java.rmi.remote. This class names in the RMIC command must be for classes that have been compiled successfully with the Java C command and must be fully package qualified. For example, running RMIC on the class file name hello impl as shown here, rmic hello impl creates the hello impl underscore stub.class file in the hello subdirectory named for the classes package. In Unix, RMIC deprecation note support for static generation of Java remote method protocol JRMP stubs and skeletons has been deprecated. Oracle recommends that you use dynamically generated JRMP stubs instead, eliminating the need to use this tool for JRMP based applications. RMIC compiler generates a stub and skeleton class files using the Java remote method protocol JRMP and stubs and class files IIOP protocol for remote objects. These class files are generated from the compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements the interface java.rmi.remote. The class names and the RMIC command must be for classes that were compiled successfully with the Java C command and must be fully package qualified. For example, running the RMIC command on the class file hello impl in Unix here, as shown here, creates hello impl underscore stub dot class file in the hello subdirectory named for the classes package. Here RMIC hello impl. The skeleton for the remote object is a JRMP protocol server side entity that has a method that dispatches call to the remote object implementation. Now we are considering the remote stub class in stub and skeleton interfaces. The stub objects are surrogates that support exactly the same set of remote interfaces defined by the actual implementation of a remote object. The class remote stub deprecated. Statically generated stubs are deprecated. Since the stubs are generated dynamically, the remote stub class is a common superclass of statically generated client stubs and provide a framework to support wide range of remote reference semantics. Stubs objects are surrogates that support exactly the same set of remote interfaces defined by the actual implementation of the remote object. The java.rmi.server remote stub class is a common superclass for stubs of remote objects. Stubs objects are surrogates that support exactly the same set of remote interfaces defined by the actual implementation of remote object. First constructor of remote stub creates a stub with a null remote reference. The second constructor creates the stub with a given remote reference ref. The setref method is deprecated and unsupported as of the Java 2 SDK standard edition version 1.2. Here the class remote stub is in the package java.rmi.server, which is in the module java.rmi. Now we are considering remote call interface. The interface remote call is an abstraction used by the stubs and skeletons of the remote objects to carry out a call to a remote object. The interface remote call deprecated, no replacement. The remote call is an abstraction used solely by the RMI runtime in conjunction with the stubs and skeletons of the remote objects to carry out the call to a remote object. The remote call interface is deprecated because it's only used by the deprecated method in Java. .rmi.server.remote.ref. Note the remote call interface is deprecated as of the Java 2 SDK standard edition version 1.2, and the 1.2 stub protocol does not make use of the interface anymore. As of Java 2 SDK, the standard edition version 1.2 stubs are now use the new invoke method, which does not require remote call as a parameter. The method get output stream returns the output stream into which either stub marshals arguments or skeleton marshals results. The method release output stream releases the output stream in some transports. This will release the stream. The method get input stream returns the input stream from which the stub marshals results or skeleton marshal parameters. The method release input stream releases the input stream. This allows some transport to release the input side of the connection early. The method get result stream returns the output stream after writing out the header information relating to the success of the call. Obtaining a result stream should only succeed once per remote call. If success is true, then result to be marshaled is a normal return. Otherwise, the result is an exception. The stream corruption exception is thrown. The stream corruption exception is thrown if the result stream has already been obtained for this remote call. The method execute call does whatever it takes to execute call. The method done allows cleanup after the remote call has completed. the skeleton interface, and the skeleton for a remote object is a server-side entity that is dispatches call to the actual remote object implementation. Interface skeleton deprecated, no replacement. Skeletons are no longer required for remote method calls in Java 2 platform version 1.2 and greater. The skeleton interface is used solely by RMI implementation. This is in the package java.rmi.server, which is in the module java.rmi. The interface skeleton is used solely by the implementation of generated by implementation of skeletons generated by RMIC compiler. A skeleton for a remote object is a server-side entity that dispatches calls to the actual remote object implementation. Note the skeleton interface was deprecated as of Java 2 SDK. The standard edition version 1.2 every 1.1 and version 1.1 compatible skeletons generated in 1.2 using RMIC-V compact, the default. The skeleton class generated by the RMIC stub compiler implements this interface. Skeletons are no longer required for the remote method call dispatch as of Java 2 SDK standard edition version 1.2 compatible versions. To generate stubs that are compatible with 1.2 or later version, use command RMIC with option -v 1.2. The dispatch method unmarshals any argument from the input stream obtained from the call object, invokes the method indicated by the operator number opnum on the actual remote object implementation object, and unmarshals the returns value or throws an exception if one occurs during the invocation. The get operations method returns an array of arrow containing operation descriptors for the remote objects methods. Now we are considering the operation class. The class operation holds a description of a method in a Java programming language for remote object. The class operation deprecated, no replacement. The operation contains the description of a Java method. Operation objects were used in Java in JDK 1.1 version stubs and skeletons. The operation class is not needed for 1.2 style stubs, hence this class is deprecated. This is in the class package java.rmi.server, which is in the module java.rmi. Note the operation interface is deprecated as of Java 2 SDK standard edition version 1.2. The 1.2 stub protocol no longer uses the old remote ref .invoke method, which takes the operation as one of its argument. As of Java 2 SDK standard edition version 1.2, stubs now use the new invoke method, which does not require operation as a parameter. The operation object is typically constructed with the method signature. Method get operation returns contents of the operation descriptor, the value with which it was initialized. The method toString also returns the string representation of the operation descriptor, typically the method signature. Now we are considering remote method invocation RMI tools in JDK tools and utilities. The tool RMIC here generates stubs and skeletons for remote objects. Now we are considering examples in command line examples in dynamic code downloading using Java RMI using the java.rmi.server codebase property. If the location of your downloadable classes is on the HTTP server named web vector in the directory export under the web root, your codebase property setting might look like this. And if the location of your downloadable classes is on the HTTP server named webline in jar file name my stuff in the directory public under the web root. If your code base property settings might look like this. And now let's suppose the location of your downloadable classes has been split between two jar files, my stuff.jar and my other stuff.jar. In these jar files are located in the different servers named webfront and webview. Your code base property settings might look like this. Now we are considering properties that are useful to set on virtual machine JVMs that export remote objects java.rmi properties, java.rmi properties, java.rmi.server.codebase. This property specifies the locations from which the classes that are published by this VM, for example, stub classes, custom classes that implement and declared return type of remote method call or interfaces used by proxy or stub classes may be downloaded. The value of this property is a string in URL format or a space separated list of URLs that will be the code base annotation for all classes located from the class path of and subsequently marshaled by this VM. Note, this property must be set correctly in order to dynamically download classes and interfaces using Java remote method invocation, Java RMI. If this property is not set correctly, you will likely to encounter exceptions when attempting to run your server or client. Now we are considering properties that are useful to set on VMs that make remote method calls. Again, the java.rmi.server.codebase. This property specifies the location from which the classes that are published by this VM, for example, custom classes that are implement an interface that is declared parameter type of a remote method call may be downloaded. The value of this property is a space separated list of URLs that will be a code base annotation for classes downloaded from class path of and subsequently marshaled by this VM. Note, classes that exist in both server's code base and client's class path will be loaded from the client's class path rather than from the server code base as intended. Remote reference layer. The remote reference layer understands how to interpret and manage references made from clients to remote service objects. Here you can see another view of RMI architecture. As you can see here, the client makes a request for remote object using client side stub. The server object receive this request from the server side object skeleton. Client initiate a remote method invocation by calling a method on the stub object. The stub maintains an internal reference to the remote object it represents and forward the method invocation request through the remote reference layer by marshalling the method argument into serialized form and asking remote reference layer to forward the method request and arguments to the appropriate remote object. Marshalling involves converting local objects into portable form so that they can be transmitted to a remote process. Each object is checked as it is marshaled and determine whether it implements java.rmi.remote interface. If it does, remote reference is used as it marshal data. If it is a remote object, the argument is serialized into bytes that are sent to the remote host and reconstructed the copy of the local object. If the argument is neither remote nor serializable, stub throws java.rmi.marshal exception back to the client. If marshalling of a remote argument succeed, the client-side remote reference layer received the remote reference and marshaled argument from the stub. This layer converts the client request into low-level RMI transport requests according to the type of remote object communication being used. In RMI, remote objects can potentially run under several different communication styles, such as point-to-point object references, replicated references, multi-thread, multi-class objects. Remote reference layer is responsible for knowing which communication style is in effect for given remote object and generating corresponding transport layer requests. In the current version of RMI, version 1.2 of Java 2, the only communication style provided out of the box is point-to-point object references. So this is the only style we here. For the point-to-point communication, the remote reference layer constructs a single network level request sent over the wire to the sole remote object that correspond to remote reference passed along with the request. On the server side, remote reference layer received the transport level request and convert it into the request for the server skeleton that matches the reference object. Skeleton converts the remote request to the appropriate method call of the actual server object, and which involves unmarshalling the method argument into the server environment and passing them to the server object. As you might expect, unmarshalling is the inverse process of marshalling the process to the client. Arguments sent as a remote reference are converted into the local stubs on the server, and arguments sent as serialized object are if converted into the local copies of the originals. If the method call generate a return value or an exception, skeleton marshals the object for transport back to the client and forward it through the server reference layer. This result is sent back to the appropriate transport protocol where it passes through the client reference layer and stub and is marshaled by the stub. Finally, handed back to the client thread that invokes the remote method. Here you can see the client process, client object, stubs, and remote reference manager here is inside the client process. Here you can see server process, remote reference manager, skeleton, and server objects are inside server process. In client process, client objects interact with stub interacts with remote reference manager. Here remote reference manager interacts with skeleton interacts with server objects, and client process and server process. So server process is interacting, and RMI transport layer is between client process and server process. Here you can see the remote reference layer for remote manager, remote reference manager in server process, and for the client remote reference manager in client process with stub and skeleton layer. You can see the stub and skeleton here. Here you can see a overview of RMI interfaces and classes. The interfaces and classes that are responsible for specifying the remote remote behavior of RMI system are defined in the java.rmi package hierarchy. The following figure shows the relationship between several of these interfaces and classes. In RMI, this is java.rmi.remote interface. In RMI, the remote interface is an interface that declares a set of methods that may be invoked from a remote Java virtual machine. A remote interface must satisfy following requirements. A remote interface must at least extend either directly or indirectly an interface java.rmi.remote. Each method declaration in remote interface or its super interface must satisfy the requirement of a remote method declaration as follows. A remote method declaration must include the exception java.rmi.remote exception for one of its superclass such as java.io exception or java.lang.exception in its throws clause in addition to any application specific exceptions. Note that application specific exceptions do not have to extend java.rmi.remote exception. In a remote method declaration, a remote object declared as a parameter or return value, either declared directly in the parameter list or embedded within non-remote object in a parameter, must be declared as a remote interface, not implementation class of that interface. And the remote exception class, the java.rmi.remote exception class is the superclass of exception thrown by the RMI runtime during remote method invocation. To ensure the robustness of applications using RMI system, each remote method declared in a remote interface must specify java.rmi.remote exception or one of its superclass such as java.io.exception or java.lang.exception in its thrown clause. The exception java.rmi.remote exception is thrown when a remote method invocation fails for some reason. Some reason for remote method invocation failures includes communication failure, the remote server is unreachable or is refusing connections. The connection is closed by the server. Failure during parameter or return value marshalling or unmarshalling. Protocol errors. The class remote exception is checked exception. One that must be handled by the caller of a remote method is checked by the compiler, not runtime exception. Especially the remote object class and its subclasses with related to remote reference layer. RMI server functions provided by java.rmi.server.remote object and its subclasses java.rmi.server.remote server and java.rmi.server.unicast remote object and java.rmi.activatable. The class java.rmi.server.remote object provides implementation for java.lang.object methods hashcode equals and toString that are sensible for remote objects. The methods needed to create remote objects and export them them available to remote clients are provided by the class unicast remote object and activatable. The subclass identify the semantics of the remote reference, for example whether the server is simple remote object or is an activatable remote object, that one that executes when invoked. The java.rmi.server.unicast remote object class defines a singleton unicast remote object whose references are valid only while the server process is alive. The class java.rmi activation.activatable is an abstract class that defines an activatable remote object that starts executing when its remote methods are invoked and can shut itself down when necessary. Here you can see a remote implements remote object, and remote object extends the remote object implements remote, and remote server extends remote object, and activatable extend remote server. Unicast remote object extend remote server. Remote exception extend IO exceptions. As an example, we can consider this one, and the remote reference layer defines and supports invocation semantics of RMI connection. This layer provides remote ref object that represent the link to the remote service implementation objects. Interface remote ref represent the handle for a remote object. A remote stub uses remote reference to carry out the remote method invocations to a remote object. And remote ref is in java.rmi.server package. As an exception example, we can consider this. If failed to initialize new remote call in deprecated method remote call, new method new call remote object option int long in interface remote ref. This is in package RMI java.rmi.activation. This is in actually java.rmi.server package. As an example too, we can consider this one. The class unicast remote object used for exporting a remote object with JRMP and obtaining a stub that communicates to the remote object. Stubs are either generated at runtime using dynamic proxy objects, or they are generated statistically at build time, typically using RMIC tool. The method export object remote int exports the remote object to make it available to receive incoming calls using a particular supplied port. The object is exported with a server socket created using RMI socket factory class. The parameters obj the remote object to be exported, and port to export the object on, and this is in package java.rmi.server. As an exception example too, we can consider remote exception. If export fails in method remote export object remote int in class unicast remote object. As an example tree, we can consider this one: creating an activatable object. The class activatable, the activatable class provides the support for remote objects that require persistent access over time and that can be activated by the system. And this is in package java.rmi.activation, and here you can see the code and implementing interface and the constructor, and here register object with the activation system, then export it to an anonymous port. As an exception example 3, now we are considering a remote ref interface in stub and skeleton interfaces. The remote reference is used to carry out remote calls on the remote object for which it is referenced. The interface remote ref, the remote ref represent the handle for remote object. The remote stub uses the remote reference to carry out the remote method invocation to a remote object. This is in the package java.rmi.serve, which is in the module java.rmi. The interface remote ref represents the handle for a remote object. Each stub contains an instance of remote ref that contains a concrete representation of the reference. This remote reference is used to carry out remote calls on the remote object for which it is referenced. The invoke remote method object array and long method delegates the method invocation to a stubs object remote reference and allows reference to take care of setting up the connection, the remote host, marshalling some representation of method and parameters, params, and the communication invocation to the remote host. This method either returns the result of the invocation on the remote object which resides on the remote host, or throws an remote exception if the call failed, or an application level exception if the remote invocation throws an exception. Note that the operation number opnum represents a hash of the method signature and may be used to encode the method for transmission. The method hash to be used for opnum parameter is a 64-bit long integer computed from the first two 32-bit values of the message digest of a particular byte stream using National Institute of Standards and Technology NIST secure hash algorithm SHA-1. This byte stream contains a string as if it was written using the java.io. Data output.write UTF method consisting of a remote method name followed by the its method description. For example, if a method of a remote interface has the following name and the signature, the string containing the remote method's name and descriptor would be following. The 60-bit hash value in the little Indian composition of a 8-byte sequence, where the first 4 bytes are the first 32-bit value of the message digest in a big Indian byte order, and last 4 bytes are the second 32-bit value of the message digest in the big Indian byte order. For example, the first two of 32-bit values of the message digest are OX BO B1 B2 B3 and OX BO b4, b5, b6, b7, and then the hash value would be ox b7, b6, b5, b4, b3, b2, b1, b0. Note this the method's new call, remote object operation array and int long, invoke remote call and done are deprecated as of Java 2 SDK Standard Edition version 1.2. The stub generated by RMC using the 1.2 stub protocol version do not use this method any longer. The sequence of the calls consisting of new call, invoke and done have been replaced by a new invoke method that makes a method object as one of its parameters. The method new call creates an appropriate call object for a new remote method invocation on the remote object obj. The operation array OP contains the available operations on the remote object. Contains available operation on the remote object. Operation number opnum is an index into the operation array which specified the particular operation for the for this remote call. The interface hash is a 64-bit value used to enforce compatibility between a stub and skeleton using the version 1.1 stub protocol. The interface hash is computed from the first two 32-bit values of the message digest of the particular byte stream using SHA-1. This byte stream contains the data as if it was written using the write int and write UTF methods in interface java.io.data output consisting of the following items: int stub version number always 1 for each next point for each remote method in order of operation number, next point UTF-8 remote method name, next point UTF-8 remote method descriptor, next point for each declared exception in lexicographic order of binary name, next point UTF-8 the name of the exception class. The interface hash value is composed of the from the message digest in the same manner as described above or for the method hash used in the invoke method. The invoke remote method remote call executes the remote call. Invoke will raise any user exception which should pass through and not be caught by the stub. If any exception is raised during the remote invocation, invoke should take care of cleaning up the connection before raising the user exception or remote exception. The method done allows the remote reference to clean up or reuse the connection. Done should only be called if the invoke call returns a successfully non-exceptional into the stub. The method getRef class returns the non-package qualified class name of the reference type to be serialized into stream out. The method remote hash code returns the hash code for the remote object. Two remote object stubs that refer to the same remote object will have the same hash code in order to support the remote object as keys of the hash table. The remote object forward a call to the hash code method to the remote hash code method of the remote reference. The method remote equals compares to remote object for equality. The two remote objects are equal if they refer to the same remote object. For example, two stubs are equal if they refer to the same remote object. Remote objects forward a call to its equals method and remote equals method of the remote reference. The method remote toString returns the string that represent the reference of this remote object. Now we are considering server-if interface. The interface server-if represents the server-side handle for the remote object implementation. The interface server is deprecated, no replacement. This interface is unused and is obsolete. The server-if represents the server-side handle for the remote object implementation. The method export object finds or create a client stub object for the supplied remote object implementation obj. The parameter data contains information necessary to export the object, such as port number. The method get client host returns the host name of the current client. When calls from a thread actively handling a remote method invocation, the host name of the client invoking a call is returned. If a remote method call is not currently being service, then server not activation server not active exception is called. Now we are considering class unicast-ref. The note there is a JDK internal dependency on the existence of these classes. Get live ref method, as it's inherited by unicast-ref2 in the implementation of javax.management.remote.rmi controller. This is in the package sun.rmi.server. Now we are considering class unicast server-if. Unicast server-if implements the remote reference layer server-side behavior for remote object exported with the unicast reference type. This is in the package sun.rmi.server. Now we are considering class live-ref. Note this is a JDK internal dependency on the existence of this class and its get client socket factory method in the implementation of javax.management.remote.rmi connector. This is in the package sun.rmi.transport. Now we are considering properties that are useful to set on virtual machines VMs that export remote object in java.rmi properties. java.rmi.dgc.least_value. The value of this property represents the least duration in millisecond granted for other VMs that hold remote references to objects which have been exported by this VM. Clients usually renew a lease when it is 50% expired, so a very short value will increase the network traffic and risk late renewals in exchange for reduced latency in calls to unreferenced. The default value of this property is 600,000 milliseconds, 10 minutes. Now we are considering properties that are useful to set on VMs that export remote object in sun.rmi properties. sun.rmi.dgc.act timeout. The value of these properties represent the length of the time in milliseconds that server-side Java RMI runtime will strongly refer to a remote object or a reference to a remote object that has been returned from the current virtual machine as part of the result of the of a remote method call until it receives a positive acknowledgement from the client that the remote reference has been fully received or processed. This timeout only applies to a failure situation in which the client fails to send acknowledgement. Setting the value too low can increase the risk of a remote object being prematurely garbage collected when only the known reference to a remote object is the one in transit as part of the remote method remote method call result. The maximum value is long.max value. The default value is 300,000 5 minutes. Now we are considering properties that are useful to set on VMs that make remote method calls. sun.rmi.dgc.client.gc interval. When it is necessary to ensure that DGC clean calls are unreachable, the remote references are delivered to timely fashion. The The value of this property represents the maximum interval in milliseconds that the RMI runtime allow between garbage collection of a local heap. The default value is 3,600,000 milliseconds, 1 hour. Now we are considering Java RMI implementation logging. So system property name sun.rmi.server.log level, logger name sun.rmi.server.ref, information logged, server side remote reference, and also you can consider as another example we can sun.rmi.client.log level property, the logger name sun.rmi.client.ref, information logged client side remote reference activity. Activation exception, the class activation exception, general exception used by the activation interface. This is in package java.rmi.activation. Now we are focusing on transport layer. The bottom layer is the transport layer, which is based on TCP IP connections between machines in a network. It provides basic connectivity as well as some firewall penetration strategies. Here you can see the unfettered use of TCP IP connections between JVMs. Here you can see the transport layer makes the connection between JVMs. All connections are stream-based network connections that use TCP IP. Even if two JVMs are running in the same physical computer, they connect through their host computer's TCP IP network protocol stack. This is why you must have an operational TCP IP configuration on your computer to run JVMs, and this diagram shows the unfettered use of TCP IP connections between JVM. As you know, TCP IP provide the persistent stream-based connection between two machines based on an IP address and port number at each end. Usually DNS is used instead of IP address, which means you could talk about TCP IP connections in the current release of RMI. TCP IP connections are used as the foundation for all machine-to-machine connections. On top of TCP IP, RMI uses wire level protocol called Java Remote Method Protocol, JRMP. JRMP is a proprietary stream-based protocol that is only partially specified, is now in two versions. First version was released with Java 1.1 version of RMI and required to use skeleton classes on the server. The second version was released with the Java 2 SDK. It has been optimized for performance and does not require skeleton classes. There are versions like RMI IIOP, which which is available in Java 2 SDK version 1.3. RMI transport layer is designed to make connection between client and server even in the face of network obstacles. While the transport layer prefers to use multiple TCP IP connections, some network configuration only allow a single TCP IP connection between a client and server. Some browsers restrict applets to a single network connection back to their hosting server. So here you can see JRE there, and host OSs are there. These are connected through the network layer, and also this JRE and remote JRE is connected with the different host OS through the network layer. As a separate description, on top of TCP/IP layer, RMI uses wire level protocol called Java Remote Method Protocol JRMP, which work like this. Now, step 1, object that require remote behavior should extend the remote object class, typically through unicast remote object subclass. The unicast remote object subclass exports the remote object to make it available for serving incoming RMI calls. Exporting the remote object creates a new server socket which is bound to a port number. A thread is also created that listens for a connection on that socket. The server is registered with the registry. The client obtains details of connecting to the server from the registry. Using information from the registry, which includes the hostname and port details of the server's listening socket, and client connects to the server. When the client issues a remote method invocation to the server, it creates a TCP/IP connection object which open a socket to the server on the port specified and send RMI header information and marshaled argument through this connection using the stream remote call class. On the server side, when the client connects to the server socket, new thread is assigned to the deal with the incoming call. Original thread can continue listening to the original socket so that additional calls from other clients can be made. A server reads the header information and creates remote call object of its own to deal with unmarshalling RMI arguments from the socket. The service call method in the transport class services the incoming call by dispatching it. The dispatch method calls the appropriate method on the object and pushes the result back down to the wire. If the server object throws an exception, server catches it and marshals it down to the wire instead of returning the value. And back on this client side, the return value of the RMI is unmarshaled and returned from stub back to the client code itself. If the exception is thrown from the server, that is unmarshaled and thrown from the stub. As an example, we can consider stream remote call. The class stream remote call, stream based implementation of the remote call interface. This is in package sun.rmi.transport. As an exception example, we can consider IO exception. This is IO exception for any other problems with IO in method object output get result stream boolean in class stream remote call. As an example too, we can consider this sample code illustrating a secure RMI connection. This is basically modified to install and use custom RMI socket factory. It uses RMI over SSL transport layer. Factory and SSL here. Using JSSE. Here interface RMI socket, RMI client socket factory An RMI client socket factory instance is used by the RMI runtime in order to obtain client sockets for RMI calls. A remote object can be associated with an RMI client socket factory when it is created or exported via the constructors or export object methods of java.rmi.server.unicast remote object and java.rmi.activation.activatable activatable. In RMI, the interface RMI server socket factory. An RMI server socket factory instance is used by RMI runtime in order to obtain server sockets for RMI calls. A RMI object can be associated with an RMI socket factory when it is created, exported via the constructed or export object methods of java.rmi.server.unicast remote object and java.rmi.activation activatable object. These are in java.rmi.server package. Here you can see make reference to SSL based registry in local registry.get registry, and here you can see a new RMI SSL client socket factory is there for SSL. As an exception example 2, we can consider IO exception. If an IO error occurs during socket creation in create sockets string int method in interface RMI client socket factory. And as an example 3, we can consider this sun.rmi property, sun.rmi.transport.tcp.read timeout. This value of the value of this property represents the time in milliseconds used as an idle time for creating TCP/IP connections the Java RMI runtime uses. The value is passed to java.net.socket.set so timeout. This property is used only for cases where a client has not dropped an unusual connection as it should in sun.rmi properties. The default value is 2 multiplied by 3600 multiplied by 1000 milliseconds, that is 2 hours. Now we are considering RMI transport protocol. The wire format for the content of the transport header are not formatted using object serialization. The wire format for RMI is represented by a stream. The terminology adopted here reflects a client perspective. Out refers to the output messages and in refers to input messages. The content of the transport header are not formatted using object serialization. The input and output streams used by RMI are paired. Each out stream has corresponding in stream. The out stream and out stream in the grammar maps to the output stream of a socket from the client perspective. An in stream in the grammar is paired with the corresponding socket's input stream. Since output and input streams are paired, the only header information needed on an input stream is an acknowledgement as to whether the protocol is understood. Other header information such as the magic number and version number can be implied by the context of stream pairing. Now we are considering format of an output stream. Alternatively, an output stream can contain an invocation embedded in the HTTP protocol. An output stream in RMI consists of transport header information followed by a sequence messages. Alternatively, an output stream can contain an invocation embedded in the HTTP protocol. The messages are wrapped within a particular protocol as specified by protocol. For the single op protocol, there may only be one message after the header, and there is no additional data that message is wrapped in. The single op protocol is used for invocation embedded in HTTP request, where interaction beyond a single request and response is not possible. For the stream protocol and the multiplex protocol, the server must respond within a byte zero x4e, acknowledging support for the protocol, and the endpoint identifier that contains the host name and port number that server can see is being used by the client. The client can use this information to determine its host name and name it if it is otherwise unable to do that for the security reasons. Client must then respond with another endpoint identifier that contains the client default endpoint for accepting connections. This can be used by the server in the multiplex protocol case to identify the client. For the stream protocol, after this endpoint negotiation, the message are sent over the output stream without any additional wrapping of the data. For the multiplex protocol, the socket connection is used as a concrete connection for the multiplex connection. Virtual connections initiated over this multiplex connection consist of a series of message as described below here. There are three types of output messages: call, ping, and DGC ACK. A call encodes a method invocation. Ping is a transport level message for testing liveness of remote virtual machine. DGC ACK is an acknowledgement directed to the server's distributed garbage collector that indicates the remote object in a return value from the server have been received by the client. Now we are considering format of an input stream. A ping ACK is the acknowledgement for ping message. There are currently three types of input messages: return data, HTTP return, and ping ACK. The return data is the result of a normal RMI call. HTTP return is return result from an invocation embedded in HTTP protocol. Ping ACK is the acknowledgement for ping message. As an example, soon we can consider interface endpoint. This is in the package sun.rmi.transport. Now we are considering interface channel. This is in the package sun.rmi.transport. Now we are considering class TCP endpoint. TCP endpoint represents some communication endpoint for an address. This is in the package sun.rmi.transport.tcp. Now we are considering a TCP class TCP channel. TCP channel is a socket-based implementation of the RMI channel abstraction. This is in the package sun.rmi.transport.tcp. Now we are considering class TCP connection. This is in the package sun.rmi.transport.tcp. Now we are considering class TCP transport. TCP transport is a socket-based implementation of the RMI transport abstraction. This is in the package sun.rmi.transport.tcp. Now we are considering properties that can be stored on, can be set on RMID in sun.rmi properties. sun.rmi.transport.tcp.localhostname timeout. The value of this property represents the time in milliseconds that the Java RMI runtime will wait to obtain a fully qualified domain name for the localhost. The default value is 10,000 milliseconds, 10 seconds. Now we are considering properties that are useful to set on VMs that make remote method calls. sun.rmi.transport.connection.timeout. The value of this property represents the period in milliseconds for which the socket connection may reside in an unused state before the Java RMI runtime will allow those connections to be freed, closed. The default value is 15,000 milliseconds, 15 seconds. Now we are considering Java RMI's implementation logging. System property name here sun.rmi.transport.loglevel. Logger name sun.rmi.transport.misc. Information logged, transport layer activity. Want thread pooling at RMI transport layer enabled by default. As a local fix, we can consider customer can set it, and with the property sun.rmi.transport.tcp.no connection pool equal true or any none value to disable thread pooling. This is the end of my presentation. Thank you very much for watching.